Hi everyone, welcome to goclasses. Before we start this session, please let me know, is the audio, video, volume, everything is fine? Let me know. Let me know. Then we will start this session. This is all-in-one session for decomposition of relations. We will see everything: lossless, dependency preserving, chess test, okay, BCNF, 3NF decomposition. Basically, all the concepts we will see. Let me know. Audio, video, everything is fine. Okay, so let's start now. And if there is any issue anytime, let me know. Okay, now we will start. So let's focus on this lecture. Okay, let's make use of this lecture fully. Okay, awesome. So let's start now. Hi everyone, welcome to Go Classes. In this lecture, we will study decomposition. This is going to be all-in-one lecture for decomposition of a relation in DBMS. We will see all the concepts related to relation decomposition, like lossless, lossy decomposition, dependency preservation, chess test, 3N of decomposition, BCN of decomposition. So all-in-one decomposition of a relation. Okay. Now let me tell you that in the previous lecture, we have seen the normal form summary. So on the Go Classes YouTube channel, you can find this lecture where we have done the discussion of normal forms, complete summary and gate PYQs, 1NF, 2NF, 3NF, BCNF, basically all in one. Okay, so this link you can find in the pinned comment, also in the description. Now let's start our lecture, that is relation decomposition. Decomposition of a relation in DBMS, or I can say decomposition of a table. So let's see the content of this lecture. In this lecture, these are the topics that we are going to discuss. We will discuss natural join of two tables, natural join of two relations. Remember, relation is also called table. Also, we will discuss relation decomposition definition. We will see lossless and lossy decomposition. We will also see dependency preservation, the chess test, and also 3NF BCNF decomposition. Okay, so all these topics we are going to discuss in this lecture. So let's start. First, we are going to discuss the topic, that is natural join of two tables. Let's see the definition. Natural join of two relations, or I can say natural join of two tables. This is a binary operation. Binary operation means this is performed between two tables, or I can say two relations. So your input must be two tables, two DBMS tables, or I can say two DBMS relations. Okay. So natural join, this is the symbol for natural join. You can see bow tie. Okay. So you can see that natural join is a binary operation, and we write it like this. This R natural join S. Now, what is the output of this natural join? So you can see the input is two tables, or I can say two relations, that is the input. The output will be that this natural join will combine the tuples of S comma R. It will combine the tuples of R comma S that are equal on their common attribute names. In this relation R, in this relation S, there will be some attributes which are common, or I can say basically the set of attributes which have the same name. Now, what this natural join will do? This will combine the tuples of R comma S that are equal. The tuples are equal on their common attribute names. Okay, so let's take example. Consider this relation. You can see we have two relations R1, R2, two tables we have. Now, we want to do the natural join of these two tables. So first you find what are the common attribute names. Means which attribute names are common, or I can say which attributes are common in these two tables. So you can see that department, this attribute is common. Okay, you can see this department attribute is in the table R1 also. This department attribute is in the table R2 also. Okay, so I can say these are the common attributes in R1 comma R2. Now what the natural join? R1 natural join R2, that simply means that we will combine the tuples of R1 comma R2 where the tuples are equal on the department attribute. Okay, you can see the tuples must be equal. We will combine the tuples of R comma S where the tuples are equal on their common attribute names. Okay, so here you can see that which tuples we will combine. So you can see this tuple has department equal to sales and this tuple also has department equal to sales. So you can see this tuple number 1, this tuple will combine with this tuple. Okay, so I can do like this, that this is the, so in the output we will get, you can see Smith, sales and Brown. Okay, and let me tell you one more thing. You can see here we have two attributes, here we have two attributes, but in the natural join output we will not write this department attribute two times. Okay, because you can see this department attribute, this is common, and we are performing the equality of this attribute. Okay, this common attribute. So you can see in the output this department attribute we will write only one time. Okay, we are not going to write this department attribute two times, we are going to write this department attribute only one time. So you can see in the output there will be three attributes. Okay, so you can see this first row, this will combine with this row because they are equal in the department attribute. Okay, which is the common attribute of these two tables. Next you can see that this tuple will combine with the first tuple. Okay, you can see because here we have department production, here also department production. So you can see this second tuple will combine with the first tuple. Okay, because they are equal in the common attribute. Next you can see that this tuple, this third tuple of R1 will combine with the first tuple of R2. Okay, so this is how they will combine. So finally you can see that in this R1 natural join R2 there will be three tuples. You can see, okay, you can see Smith, sales and Brown. Next, black, production and Mori. You can see white, production and Mori. So very simple, this will be the output of natural join. Let's see one more example. We have two tables S comma T. Okay, in this table S comma T we want to perform the natural join. So what will be the output of natural join? This natural join output we want to find. So you can see I told you that natural join, that simply means we will combine the tuples of S comma T where those tuples are equal in the common attributes. Okay, you can see what are the common attributes of S comma T. You find the attributes which have the same name in S comma T. Okay, common attribute names in S comma T. So you can see that grade. You can see this grade, this attribute is common. Okay, this grade attribute, this attribute is common in both the tables. Okay, so what we are going to do in the natural join, we are going to combine the tuples of S comma T where the tuples are equal in this common attribute. Okay, so very simple, this first tuple of S, this will combine with this first tuple of T. Okay, because here grade is equal to 2, here also grade equal to 2. So this first tuple will combine with this first tuple. Next, this second tuple of S will combine with the second tuple of T because here the grade is 3, here the grade is 3. Okay, so these will combine. Next you can see this tuple, this third tuple of S will combine with the third tuple of T because you can see here grade is 4, here grade is 4. So these two tuples will combine. And this last tuple, fourth tuple of S will combine with the first tuple of T because here grade is 2, here grade is 2. So they will combine. Okay, so you can see that this tuple will combine with this tuple. So finally in this natural join there will be total, in the output there will be total 4 tuples. Okay, so let me show you the output. You can see the output will be, this table will be the output. So I can say that this is the output R, this table R, this is basically equal to S natural join T. Okay, and I told you that in the natural join output we don't write this common attribute two times. In this S comma T, this grade attribute, this is the common attribute, this is the attribute with the same name in both the tables. So this attribute we are not going to write two times, we will write it only one time. Okay, so in this natural join, in the output there will be 5 attributes. This is the schema of natural join. Okay, you can see, so name, SSN, DOB, grade and salary. So there will be 5 attributes in the output, and you can see there are 4 tuples in the output. Okay, you can easily see this tuple is combining with this tuple, so the output will have C106 2987 280. So you can see this tuple we will get in the output. Okay, so very simple concept. Let's see this example. Here you can see we have two tables R comma S and we want to perform the natural join R natural join S. Then what we will do? First we will find what are the common attributes of R comma S. So here you can see that in this table R we have attribute ABCD, in the table S we have attribute BDE. So B comma D, BD, these are the common attributes. Okay, so in both the tables, if you see what are the common attribute names, or I can say common attributes, so those are B comma D. Okay, so if you do the schema intersection, basically if you see the R intersection S, the schema intersection, okay, so that will be basically B comma D. I can say the schema of R intersection with the schema of S, so that will be basically, that will be B comma D. Okay, the schema intersection will be B comma D. Basically B comma D, these two attributes are common. Okay, so in the natural join, what we will do, we will find the equality. Basically we will join the tuples where the tuples are equal in the common attributes. Okay, so you can see the first tuple, look at the first tuple here, BD, these are 1 comma A. Okay, so you can see this 1 comma A. Now in this table you check, is there any tuple where BD is equal to 1A? Yes, here 1A, here 1A. Okay, so very simple, this first tuple of R will combine with these two tuples. Okay, very simple. So you can see in the output we will get these two tuples. You can see alpha 1 alpha A alpha. Okay, and remember in the output we will not write these common attributes two times. We will write them only one time. So you can see A, B, C, D, these B comma D, these are common. So in the output we will write B comma D only one time, and the remaining attributes are A, B, C, D, and there is attribute E here. So the output schema will be A, B, C, D, E. Okay, and very simple, you can see this first tuple, because here BD value is equal to 1A. Okay, so in this table you find where is BD equal to 1A. So you can see that in these two tuples, first and third tuple, the BD equal to 1A. So finally this tuple will combine with these two tuples. Okay, and in the output you can see we will get these two tuples in the output. Next, what about this second tuple? In this second tuple the BD value is 2 comma A. So in this table S you find those tuples where BD equal to 2A. There is no tuple where BD equal to 2A. Remember in this tuple the B value is 2 but the D value is not A. Okay, we have to check the equality of common attributes, all the common attributes. Okay, see in this second tuple the B value is 2. In this table the B value is 2, but remember the common attributes are BD. We have to check the equality of all the common attributes. Okay, so if the common attributes are B comma D, then we have to check the equality of both the common attributes B comma D. Okay, so you can see this tuple will not combine with any tuple of S. Very simple. Next, what about this third tuple? In this tuple we can see that the BD value is 4B. In this table S, is there any tuple where BD value equal to 4B? No. So you can see this tuple will not combine with any tuple of S. Okay, let's see the next. You can see that this tuple has BD value equal to 1A. So this tuple will combine with the first tuple, also with the third tuple. So you can see we will get these two tuples in the output. Okay, we will get alpha 1 gamma A alpha, alpha 1 gamma A alpha. Also we will get alpha 1 gamma A gamma. Okay, alpha 1 gamma A gamma. Very simple. Okay, what about the last tuple? Will it combine with any tuple of S? So you can see in this tuple, in the last tuple, the BD value, the common attribute value, all the common attribute value, that is 2B. Okay, now in this table is there any tuple where the BD value is equal to 2B? Yes. Okay, you can see. So you can see that this last tuple of R will combine with this fourth tuple of S, and finally we will get this tuple in the output, that will be delta 2 beta B delta, delta 2 beta B delta. Okay, so this is the idea. I hope you understood. Okay, so that's it. This is the natural join. You can see this is the symbol for the natural join, and what we do, we will combine the tuples of R1 comma R2. Okay, in the natural join, R1 natural join R2, that simply means combine the tuples of R1 and R2 where the tuples are equal in the common attributes. So you can see we will equate the attributes of the same name. Okay, in R1 comma R2 we will find the attributes which have the same name, we will find the common attributes, and we will equate the attributes of the same name. Very simple. And remember, in the output we will project only one copy of the common attributes. In the output, the common attributes we will write only one time. Okay, so you can see we will project only one copy of the common attributes. Okay, so this example you can easily see that in this example we are doing the natural join of employee comma department. And what are the common attribute names? So in these two tables, the common attribute, that is department name, you can see this attribute has the common name in both the tables. Okay, so what we will do, very simple, you can see this tuple will combine with this tuple because they have the same value in the common attribute. You can see this tuple will combine with this tuple, this sales tuple will combine with this, and this finance tuple will combine with this. So in the output there will be total 4 tuples, and you can see there is no tuple of employee which will combine with the last tuple of department. Okay, very simple. So this was your natural join. I hope you understood the concept of natural join of two tables. Let me see if there is any doubt. So far everything is clear? Please let me know. After every topic, I will check your chat. If you have any doubt, let me know. In this lecture, let's focus on this lecture. Okay. In this particular lecture, do you have any doubt? My complete focus is on this lecture, and I suggest that you also have your complete focus on this lecture. Okay, because this is an important lecture in the GATE exam. There are many questions. Okay. So let's understand this. So far everything is clear. Okay, very good. Now let's move on. So in the natural join, we equate the attributes of the same name. What if there is no common attribute? You might be thinking that if the two tables have no common attribute name, or I can say there is no common attribute in both the tables, then how to do the natural join? What if no common attribute with the same name in two relations, then how to do the natural join? So let me tell you the answer. That is, if there is no attribute with the same name in the two tables, then we will combine every tuple with every tuple. Okay, so you can see that if no common attribute, then combine every tuple of R with every tuple of S. Okay, so you can see that these two tables, table R comma S, here we can see that there is no common attribute, or I can say there is no attribute with the same name. In the table R we have A comma B, these are the attributes. In the table S we have C, D, E, these are the attributes. So there is no attribute with the same name in these two tables. Then how to perform the natural join? So in this situation, the natural join will be performed like this, that we will combine every tuple of R with every tuple of S. Okay, very simple point, that if there is no common attribute, if there is no attribute with the same name, then we will combine every tuple, every row of S with every row of R. Okay, so this is the point. So finally here I can say that you can see this row will combine with all the 4 rows, and this row will combine with all the 4 rows. There will be total 8 rows in the output. Okay, so you can see when we combine every tuple of R with every tuple of S, this is called Cartesian product, or I can say cross product. So you can see that if there is no common attribute in two tables, then this natural join, this will become the cross product. Okay, so in this situation I can say that natural join, that simply becomes the cross product. Okay, if there is no common attribute in this type of situation. So I can say if there is no common attribute, if no common attribute with the same name. Okay, very simple. I hope you understood. The next topic is decomposition of a relation. This is a very important concept from the GATE exam point of view. So let's discuss this. What is decomposition of a relation? You have a relation R. Okay, so let's assume this is the schema. There are, let's assume that 5 attributes A, B, C, D, E. Okay, so this is the schema of relation R, and we want to decompose this relation. The name itself is telling you decomposition. So we will decompose this relation into sub-relations. Okay, we will decompose this relation into smaller relations, or I can say sub-relations. So you can see this R1. The schema of R1 will be subset of schema of R. So remember, in this R1, the attributes will be subset of the attributes of R. Okay, so for example, maybe you can have attribute AC here. Okay, in the table R1, we have the attribute AC. Okay, and table R2, the table R2 schema, that will be subset of schema of R. Okay, so in this R2, let's assume that we have attribute ACD, okay, or ABD. So, and we have R3. This is also sub-relation of R. The schema of R3 will be subset of schema of R. So the attributes in R3, that will be subset of attributes of R. Okay, so for example, let's assume we have B, D, E. Okay, so now this is called decomposition, but there is one important property of the decomposition, that is that all the attributes of R, they must be preserved. Means basically if you do the union of all these decomposed schema, all these sub-relations, if you do the union of the schema of these sub-relations, then we should get the schema of R. Okay, so this additional property is there. You can see that every attribute of R should be preserved. You can see A, C, B, D, E. So all the attributes are preserved. This is called decomposition. Okay, this is called decomposition of R. So in the decomposition definition, there is one important point, that is all the attributes of R, this relation, every attribute of relation R should be preserved. Or I can say, if you do the union of schema of these sub relations, these decomposed relations, then we should get the schema of the original relation. Okay, so this is the idea, that if you do the schema union, if you do the union of schema of Ri, then that should be the schema of R. Okay, so this is the part of definition of decomposition. Remember, means if there is an attribute which is not preserved, for example, let's assume this attribute E, this attribute E is not preserved. You can see that in these sub relations we don't have attribute E. Now this is not called decomposition. Okay, now we will not call it decomposition. I hope you understood. So decomposition definition includes this attribute preservation property, that attributes must be preserved. So this is the concept of decomposition of a relation. So let me generalize this. We have a relation R and there can be n attributes, A1, A2 and so on, n attributes. So you can see this is the schema of the relation R, and we want to decompose this relation R into sub relations. Okay, into two or more sub relations. You can decompose into two relations, or you can decompose into 3, 4, any number of sub relations you can create. Okay, so we want to decompose this relation into some, let's assume, k number of sub relations. Okay, so like for example, we want to decompose into R1, R2, R3 and so on, Rk. Okay, so these are the sub relations. Now what is the property? Two properties must be satisfied, that all these sub relations, the schema of all these smaller relations, sub relations, that should be subset of the schema of R. Okay, so I can say that schema of Ri, okay, that should be subset of schema of R. Okay, means the attributes of all these sub relations, they should come from the relation R. For example, the attributes of R1, they must be present in the R. Okay, the attributes of R2, they must be subset of attributes of R. The attributes of Rk, they must be subset of attributes of R. So this is the first property. Okay, and the second property, if you do the union of schema of all these sub relations, then we should get the schema of the original relation. So the union of schema of Ri, that should be equal to schema of R. Okay, now this is called decomposition. Okay, this complete thing, this is called decomposition. This is known as decomposition of relation R into sub-relations R1 to Rk. Very simple point. So you can see the definition of decomposition. So suppose that we have a relation that contains n attributes A1 to An. Then a decomposition of R, that will consist of, we will replace this R by two or more sub-relations. Okay, we are decomposing the relation R into two or more sub-relations such that each new relation, each sub-relation will contain a subset of attribute of R. Also, every attribute of R should appear in at least one of the new relations. Okay, so this is the complete definition of decomposition. Okay, you can see here also the decomposition of relation schema R. So this is the relation schema R that has n attributes. Okay, so decomposition simply means that we will replace this relation R with some sub-relations. Okay, two or more sub-relations such that each sub-relation schema should be subset of the schema of R. Okay, and also if we do the union of schema of all these sub-relations, then we should get the schema of R. Okay, very simple. Now let's move on. Let's see these examples. So we have a relation R ABCD. The following are possible decompositions of R. Okay, you can see that this is a decomposition of R where we have AB, CD. Okay, so we are decomposing this relation into two sub-relations. Okay, you can easily see that if we do the union of both these sub-relations, the schema of sub-relations, then we will get the schema of R. Basically, every attribute is preserved. Okay, all the attributes of R, those are preserved. You can see A, B, C, D. So this is a decomposition of relation R. Next, you can see AB, ACD. This is also decomposition of relation R. Okay, because you can see every attribute of R is preserved, and you can see that every sub-relation is a subset of the schema of R. Okay, next you can see D3, A, BCD. This is also decomposition of R. Also this AB, BC, CD, AD. This is also decomposition of relation R. Okay, because you can see that each sub-relation, schema of every sub-relation is subset of schema of R, and also every attribute of R is preserved. Every attribute of R appears in at least one of the sub-relations. Okay, so all of them, these are the decompositions of relation R. Now let's see the definition of binary decomposition. The name itself is telling you binary decomposition means decomposition of a relation into two sub-relations. Okay, we are decomposing our relation R into two sub-relations, not 3, not 4. Okay, so you can see we decompose a relation R by replacing this relation R. We will replace this relation R, okay, using two sub-relations. And the same property, remember, every attribute of R must appear in at least one of the sub-relations. And if you do the union of both the sub-relations, the schema of sub-relation, if you do the union, then you should get the schema of R. So this is called binary decomposition. Basically, binary, that simply means that we are decomposing a relation into two sub-relations. I told you that attribute preservation, that is part of definition of decomposition. If attribute preservation does not happen, then we cannot call it decomposition. Okay, so remember attribute preservation property. What it means? It means that every attribute of R will appear in at least one of the sub-relations. Okay, means no attribute is lost. Very simple point. So this is called attribute preservation property, and this is part of definition of decomposition. Now we will see what is lossless decomposition and what is lossy decomposition. And this is a very important topic. So let's start. But before that, let me know, is there any doubt? Rohit is saying that shouldn't we say that subset should be non-empty also? Yes, it should be non-empty also. Okay, because if there is no attribute in a relation, we can't even call it relation. Okay, you must have at least one attribute in every sub-relation. Okay. The next topic is lossless decomposition and lossy decomposition. So let's see. The name itself is telling you lossless simply means that no loss of information, and lossy, that means loss of information. Okay, so let's see what is lossless decomposition. Lossless decomposition, that simply means there is no loss of information. What it means? It means that if we combine, when I say combine, it means natural join. Basically, when we do the natural join of decomposed relations, then we should get exactly the original relation. Okay, this is called no loss of information. That if we combine, if we do the natural join of sub relations, okay, then we should get exactly the original relation, exactly. Now what is lossy decomposition? This means loss of information. What it means? It means that when we combine, when we do the natural join of decomposed relation, then we may get extra tuples which were not present in the original relation. See, in the original relation, let's assume there is a tuple which is not present. But when we combine the decomposed relation, when we do the natural join of decomposed relation, and if we get some extra tuple which is not present in the original relation, then this is loss of information. We are getting wrong information. Remember, we are getting extra tuples. So we are not losing the tuples. Okay, we are losing the information. We are getting wrong information. So that is called loss of information. We are not losing the tuples. So please understand that when I say lossy decomposition, when I say that we are losing the information, it does not mean that we are losing the tuples. Every tuple of original relation we will get, but some extra tuples we can get. If we are getting some extra tuples which were not present in the original relation, then we will call it loss of information, loss of knowledge. Okay, we are getting wrong information, wrong knowledge we are getting. So that is called loss of information. So lossy decomposition does not mean loss of tuples. Lossy decomposition means we are getting extra tuples which are not present in the original relation. So we are having loss of information, loss of knowledge. We are getting wrong knowledge, wrong information. Okay. So let's see what is lossless decomposition. The name itself is telling you lossless, means there is no loss of information. We say that a decomposition is lossless if we can recover the original relation by natural joining the decomposed relation. Okay, means when you do the natural join of the sub relations, then we should get exactly the original relation. Okay, so very simple, no information should be lost from the original relation during the decomposition. And you can see when we join them, when the sub relations are joined back, when we do the natural join of the sub relations, then the same relation, the original relation we should get. Okay, so let's see this example. Here we have a table R. Okay, let me call it table R. The schema of table R, that is ABC. This is the table R. Now we are decomposing this table into two tables. Okay, you can easily see that every attribute appears in at least one of these sub relations. Okay, and you can see that these two tables, the schema of these two tables, that is subset of schema of R. Okay, so this is the decomposition. Now we are decomposing this relation R into R1 comma R2. Okay, the schema of R1, that is A comma C, and the schema of R2, that is B comma C. Okay, now if you do the natural join of these decomposed relation, then what we will get? Let's do the natural join. Remember, to do the natural join, we will see the common attribute. Okay, so you can see in these two relations the common attribute is this attribute C. Okay, the attribute with the same name, that is attribute C. Okay, so when we do the natural join, then we will combine the tuples of R1 with tuples of R2 such that the tuples are equal in the common attribute. Okay, so you can see that this tuple has attribute C value equal to C1. Okay, and in this tuple also the attribute C value is equal to C1. So you can see this tuple will combine with this tuple, and you can see this tuple will combine with this tuple. Okay, very simple. So finally in this output, okay, in the natural join, I can say that R1 natural join R2, if you see, then that is exactly same as R. Okay, that is exactly same as R. Okay, this is called lossless join decomposition, or I can say this is lossless decomposition. You can call it lossless decomposition, or you can call it lossless join decomposition. Both are same. Okay, so the idea of lossless, that means that we are not losing any information. Okay, when we do the natural join of the decomposed relation, then we should get the original relation, exactly the original relation we should get. Okay, so you can see here R1 natural join R2, that is equal to R. So this is the definition, this is the idea of lossless join decomposition. Let's see what is lossy join decomposition. Again, you take the example. Here we have the table R. Okay, the schema of the table R, that is ABC. There are three attributes. We are decomposing this table into R1 comma R2. R1 has two attributes AB and R2 has two attributes AC. Now let's perform the join, the natural join. Okay, so let's see what is R1 natural join R2. So what we will do, we will find what are the attributes with the same name, what are the common attributes. So the common attribute is attribute A. Okay, now in the natural join, we will combine the tuples of R1 comma R2 which are equal in the common attribute. So you can see this tuple will combine with this tuple. Also you can see this tuple will combine with this tuple also. Similarly, here the attribute A value equal to A1. So this tuple, this second tuple of R1 will combine with first tuple of R2 also with the second tuple of R2. So finally I can say in the output we will get these four tuples. Okay, now you notice one thing, that this tuple is in the original relation, that is fine. But you can see that this tuple is not in the original relation. Okay, also you can notice that this tuple is not in the original relation. Okay, so look at these two tuples. These two tuples are not present in the original relation. This is the original relation. This is the original relation, and you can easily see that these two tuples that we are getting when we do the natural join of the decomposed relation, then these two tuples that we are getting, these are spurious tuples, extra tuples, which are not present in the original relation. Okay, so this is called lossy join, means we are losing the information, we are getting wrong information, wrong knowledge. So this is called lossy join. Okay, so and remember these extra tuples that we are getting which are not present in the original relation, these are called spurious tuples. These are called spurious tuples. Either you can call them spurious tuples or you can call them phantom tuples. Okay, these are also called phantom tuples. Phantom tuples, or I can say spurious tuples. Okay, so these extra tuples which are not present in the original relation, these are called spurious or phantom tuples. Okay, and here you can easily see that the natural join of R1 comma R2, that is not same as R. So we are losing the information, we are getting the wrong information, wrong knowledge. So this is called lossy join decomposition. Okay, let's see this example. This is also example of lossy join decomposition. Okay, this is the original relation. We are decomposing into two sub-relations. Now, when we do the natural join of these two sub-relations, then we will get some extra tuples which are not present in the original relation. Okay, let's see. For example, you can see when we do the natural join of these two tables, then for the natural join, first you find what are the attributes with the same name. So you can see the common attribute is name. Okay, now you can see this tuple will combine with these two tuples, because you can see this tuple has the name equal to Kim. Also these two tuples also have name equal to Kim. So very simple. Next you can see this tuple will combine with these two tuples. So in the output these four tuples we are getting. But remember one thing, in the original relation we don't have, for example, you can see that we don't have this tuple. Okay, so you can easily see that in the original relation which tuples we do not have. So in the original relation which tuples we do not have here? Yes, this 5 7. Yes, okay, this tuple we don't have in the original relation. Also you can easily see that this tuple we don't have in the original relation. Okay, so these two tuples we don't have in the original relation. These are called spurious tuples. Okay, so I can say that these are called spurious tuples. So this is the example of lossy decomposition. We are losing the information, we are getting the wrong knowledge, wrong information. Okay, a student is asking, is it possible that we can lose the information? A student is asking, can we lose the tuples? No, we can never lose the tuples. Okay, when you have a relation R and when you decompose this relation R into R1, R2, R3, R4, okay, now if you do the natural join of these decomposed relations, then remember we can never lose a tuple. Means every tuple of R we will get, but some extra tuples we may get. Okay, if we do not get any extra tuple, basically then we will call it lossless. And if we are getting some extra tuple which are not present in the original relation, then we will call it lossy. Okay, but remember we will never lose a tuple. This point, I will come back to this point, but you will never lose a tuple. Let me tell you that these are the different names for the same concept. We can call it lossless decomposition, or you can call it lossless join decomposition, or we can call it non-additive join decomposition, or we can call it non-additive decomposition. The name itself is telling you lossless. That simply means there is no loss of information. We are not getting any spurious tuple. And similarly, non-additive means basically non-additive. Name itself is telling you that we are not getting any additional tuples. Okay, so these are different names for the same concept. Similarly, this lossy decomposition, we can also call it lossy join decomposition. So remember, lossless decomposition, that means there is no loss of information. When we do the natural join of decomposed relations, then we should get exactly the original relation. This is the definition of lossless decomposition. Okay, so let me tell you that this relation R, this is the original relation, and you are decomposing into R1, R2, R3, Rk. Then when can I say that this decomposition is lossless? So this is our decomposition. This is the decomposition D. Now when can I say this decomposition is lossless? Okay, so I can say this decomposition D is lossless. That means when we do the natural join of all these decomposed relations, then we must get exactly the original relation. Okay, so you can see that this R1 natural join R2 natural join R3 and so on, natural join RK. Okay, RK. Then what we should get? We should get the original relation. Okay, so very simple. This must be equal to R. This is the definition of lossless decomposition. Okay, very simple. So this decomposition will be lossless if when we do the natural join of the decomposed relations, then we should get exactly the original relation R. Okay, then we will call it lossless decomposition. Like here in this example, you can easily see. Okay, so this is the relation R. The schema is ABC. This is the schema. This is the original relation. Okay, we are decomposing into R1 comma R2. So this is the relation R1. This is the sub relation. Okay, remember this sub relation, what I can say? Basically, we are projecting the attribute AC from the original relation. Yes or no? Okay, so this relation R1, I can also call it pi A comma C of R. This is how I can write. Okay, because remember what this simply means? This simply means that we are projecting the attributes AC in this R1. Okay, from the original relation, we are taking the attribute AC. We are taking the attribute AC, then we are getting this R1. So I can say this R1 equal to pi AC of R. Okay, remember what it means? It simply means that from the relation R, we are taking the attribute A comma C. And similarly here, this is the relation R2, where we are taking the attribute BC from the relation R. Okay, so this I can write, remember, I can write it pi. Pi means project. We are projecting the attribute A comma C, B comma C. We are projecting the attribute B comma C from R. Okay, and remember, when I do the natural join of these two, means pi AC of R, when I do the natural join with pi BC of R, then we are getting the relation R. Okay, we are getting the exactly the original relation R. So this is the definition of lossless decomposition. Okay, I hope you understood. Very simple. So this is lossless. Okay, so this is the definition of lossless. You can easily see that we are decomposing this relation R into sub-relations R1 to Rk. Okay, then when can I say this decomposition is lossless? This decomposition will be lossless if for every instance, remember, whatever instance of R you take, for every instance what should happen? That when you combine, when you do the natural join of the decomposed relations, then we should get the original relation. Okay, so this is the definition of lossless. And remember one thing, that for every instance this should happen. Whatever instance you take, whatever snapshot, whatever instance of this original relation R you take, then it must happen that when I do the natural join of the decomposed relations, then we must get the original relation. Okay, and this should happen for every instance. Okay, this should happen for every instance, means this must happen for every instance of R. For every instance of R, of the relation R. Okay, now let's move on. And what about the lossy decomposition? Okay, we have already seen that lossy decomposition, that simply means that we may get extra tuples. Okay, we may get extra tuples. When I say we may get extra tuples, what it means? It means that for at least one instance, for some instance, we should get extra tuples. Okay, so please understand, when I say lossy decomposition, it does not mean that for every instance, whatever instance you take, you will always get some extra tuples. No. For some instance, for at least one instance of R, when we do the natural join of the decomposed relations, then we must get spurious tuples. Okay, and this should happen for at least one instance of R. So this is a note. Note that in a lossy decomposition of R, for some instance of R, please understand, for some instance of R, what will happen? We will get spurious tuples when we do the natural join of the decomposed relations. Okay, but it may not happen for all the instances. Okay, it will happen for at least one instance. It is not necessary that it will happen for all the instances of R. Okay, very simple. So let's move on. This example, you can see we are decomposing this relation R into R1 comma R2. Okay, you can see this is a decomposition. Every attribute of R is preserved. All the attributes A, B, C, D of R, all the attributes of the original relation, they appear in at least one of the sub relations. Okay, now let's check. This is a lossy decomposition or lossless decomposition. So very simple. What you will do? You will do the natural join of these two decomposed relations. Okay, so tell me, we will get some extra tuples or not? Definitely we will get some extra tuples. Okay, you can check it out. Okay, let's find the natural join. So this is the natural join, let me tell you, because some people they use this star symbol for the natural join. Okay, so this natural join, some people they use the star symbol also, but the common symbol is this natural join. So remember, this symbol is for the natural join. Okay, this is not a, I can say this is not a famous symbol. Okay, but very rare, I can say very few authors, okay, they use this symbol, but actually this is the most popular symbol. This bow tie symbol, this is the most popular symbol. So here you can easily see this relation we are decomposing into R1 comma R2, and when we do the natural join of R1 comma R2, then we are getting some extra tuples which are not present in the original relation. So this is a lossy decomposition. Okay, this is a lossy. Very simple. So let's see the conclusion. We have a relation R and the decomposition of R into 4 sub relations R1, R2, R3, R4. So this is the decomposition of the relation R. Then when can I say that decomposition is lossless? This relation I am decomposing into 4 sub relations. When can I say this decomposition is lossless join? This decomposition will be called lossless if for every instance of R, what should happen? Remember, for every instance of R, what should happen? That when we do the natural join of these sub relations, we must always get the original relation. Okay, so very simple. For every instance of R, this should happen. This should happen that when we do the natural join of decomposed relations, then we must get the original instance. We must get the original instance. Okay, so I hope this point is clear. When we do the natural join of the decomposed relations, then we must get the original instance. Okay, and this should happen for every instance R. When can I say decomposition is lossy? Lossy simply means that for some instance, what should happen? When we do the natural join of decomposed relations R3, R4. So when we do the natural join of the decomposed relations, then remember, for some instance R, what should happen? We should get some spurious tuples. We should get some extra tuples which are not present in the original instance. Okay, so this should happen for some instance R. Please understand, not for every instance, for some instance. Okay, this should happen for some instance R. Then we will call it lossy join decomposition. Means when we do the natural join of the decomposed relation, then we are getting some spurious tuples. So you can see this is superset of R, proper superset of R. Okay, and remember, whatever decomposition you take, because either your decomposition can be lossless or it can be lossy. Okay, our decomposition will be either lossless or it will be lossy. So I can say, if we combine these two, means if we consider every decomposition, whether it is lossless or lossy or whatever, so you can see in every decomposition, for every instance, what will happen? It will happen that when we do the natural join of the decomposed relations, then that will be superset of instance R. Okay, I hope you understood. So this is the idea. So remember, in every decomposition, for every instance, this will happen that when we combine the decomposed relations, then that will be superset of R. If this is proper superset of R, then we will call it lossy. If it is equal to R, then we will call it lossless. Okay, and one more thing, when you say that decomposition is lossy, then it simply means that for some instance, this proper superset you should get. Okay, for at least one instance you should get this proper superset. Okay, let's solve this question. let R1 R2 to Rn be a decomposition of schema U. Let U small u be a relation. So basically this is talking about instance. So this small u, this is the instance of this schema capital U. Okay, and the question is saying that this Ri, that is basically this is the instance. Okay, so remember, for example, for this R1 the instance is small r1, for this R2 the instance is small r2, like that. Okay, so I hope you understood. So you can see that basically we are saying that schema is U. Okay, schema is capital U, and for this schema the instance is small u. The instance is small u. Okay, similarly you can see these sub relations also have instances, that is small r1. So you can see this schema is capital R1 and the instance is a small r1. Okay, similarly you can see that this schema is capital Rn and the instance is a small rn. Okay, so the question is asking that if this is your decomposition, then which statement will be true? This is the question. So tell me, which statement will be true? I told you that whatever decomposition you take, for every instance, what will happen? It will happen that when you do the natural join of the decomposed relation, that will be superset of the original instance. Okay, yes or no? So the answer will be option A. This will be the answer. Remember, the question is not talking about lossless or lossy. The question is not asking for lossless decomposition. The question is not asking for lossy decomposition. Okay, so the answer that will be option A. Means when you do the natural join of the decomposed relation, that will always be superset of the original instance. Okay, I told you that we will never lose a tuple. Okay, if you remember, I told you that we will never lose a tuple. So please understand, this is a note, important note, that whatever decomposition you take, okay, this is the relation R. Okay, in this relation R, remember, whatever decomposition you take, then when you combine the decomposed relations, then we will never lose a tuple. Okay, this relation R, then remember, in any decomposition we will never lose a tuple. I hope you understood this point. So remember, this relation R we are decomposing into R1, R2 and so on, Rk. Okay, then here let's assume this has instance. Let's take an instance R of capital R. Okay, for this also let's take instance. Okay, and this is instance Rk. Remember how to find this R1? This R1, how to find this R1? So let me tell you this Ri, that basically how to find Ri, that will be basically the projection of attributes of R. Yes or no? You can see this Ri, this instance, how to find this instance? So this instance we will find from the instance of R, remember. So okay, it will be like pi. Okay, from R, basically we are taking the attributes of R1, of Ri. So like this, I hope you understood. Okay, so this is just a small point, don't worry about it. So this is your Ri. Basically we are projecting the attributes of R, right? Okay, so here remember, we will never lose a tuple when we combine the decomposed relations. So if I do R1 natural join R2 natural join and so on natural join Rk, when we do the natural join of all the decomposed relations, then remember, we will never lose a tuple of R. That means this will be superset of capital, this will be superset of this instance R. I hope you understood. Okay, is this point clear? So we can take instances here. So in this question also, remember, the answer will be option A. What about option B? When can I say answer will be option B? Answer will be option B for lossless. Okay, yes or no? Remember, this option B, that will be your answer if the question is talking about lossless decomposition. If the question is talking about lossless decomposition, then the answer will be option B. Okay, and what about option D? The answer will be option D for lossy. Okay, for some instance. For some instance, you can see this will happen in the lossy. I hope you understood. Now let's move on. So far, is there any doubt? Let me know. Please let me know. Is there any doubt so far? A student is saying, do we always talk about instance? The answer is yes. See, all these concepts, they are defined on the schema. The definition is always using the schema, but we will apply them on the instances. Okay, is this clear? But remember, all the concepts that we study, like decomposition, lossless, lossy, okay, all these concepts, they are defined on the schema. Now, so far, we have seen the idea of lossless decomposition, lossy decomposition, but remember, now onwards, we are not going to use instances. Because I told you that all these concepts, these are defined on the schema. So now onwards, okay, we are not going to use instances. Now onwards, every concept that we study, every definition that we see, that will apply on the schema. So please understand, this is a very important point, that all these concepts, decomposition, lossless decomposition, lossy decomposition, dependency preservation, okay, all these concepts, these are defined on the schema. So far, to understand the idea, what is the meaning of lossless, what is the meaning of lossy, we have taken instances. Okay, with the help of instances, we have seen the concept, we have seen the idea of the concept. But remember, now onwards, we are not going to use instances. We will only use schema. Okay, to check whether the decomposition is lossless, we will check the schema only. To check whether the decomposition is lossy, we will check the schema only. We are only going to use schema now onwards. We are not going to use instances from now onwards. The instances we have taken just to explain the concept. Like we are getting some extra tuples for some instance, then we are calling it lossy. We are getting wrong information. We are calling it loss of information. Okay. So now onwards, everything we will define, everything we will study over the schema only. Is this doubt clear, Rohit? Rohit is saying, is there a term like proper superset? Yes, of course there is a term, proper superset. Okay, for example, you can see this 1, 2, 3. This is a proper superset of 1, 2. This is a concept. This is proper superset. Proper superset. This is a term. This is a concept. This is a terminology. This is a valid terminology in the set theory. Okay, let's move on now. Now let's check how to check if a binary decomposition is lossless or lossy. Remember, we are going to see how a binary decomposition means we are decomposing a original relation into two sub-relations. So how to check if a binary decomposition is lossless or lossy? And this is very easy. So let's see. You can see we are decomposing the relation R into R1, R2. So this is called binary decomposition because we are decomposing the relation into two sub-relations. Now, this decomposition, this binary decomposition will be lossless. When can I say it will be lossless? It will be lossless if and only if the set of common attributes of R1, R2 that should be super key in at least one of R1, R2. So you can see this set of common attribute of R1, R2 that must be a super key in either R1 or R2 or both. Okay, so means this decomposition, this binary decomposition will be called lossless if you do the schema intersection of R1, R2, if you find the common attribute, the set of all the common attributes of R1, R2 that must be super key in at least one of them, then we will call it, then we will say that this decomposition is lossless. Okay, so you can easily see that a decomposition of R into R1, R2, basically binary decomposition is lossless if and only if when you find the set of common attributes of R1, R2, that simply means you are doing the intersection of the schema. Okay, so we are finding the common attributes of R1, R2 that must be super key in R1 or R2 or both. So you can see the set of common attributes, they must determine R1 or they must determine R2, right? Okay, so you can see that this R1 intersection R2, this should determine R1 or this should determine R2 or both. Okay, so this is the definition of lossless. Very simple. So all you need to do is just check the set of common attributes of R1, R2 is that a super key in at least one of these two tables. Okay, if yes, then I will say that this decomposition is lossless, otherwise the decomposition is lossy. Okay, so let's consider this example. The relation R is given to us. There are 5 attributes. This is the schema of the relation R, and these are the functional dependencies. Is the following decomposition is lossless? So this decomposition is given to us R1, R2. You can see R1 has 3 attributes ABC, R2 has 3 attributes ADE. So this is a binary decomposition. We are decomposing relation R into two sub-relations R1, R2. Now, how to check if a binary decomposition is lossless or not? So what we will do? We will see whether the set of all common attributes of R1, R2, that is a super key in at least one of R1, R2. So what are the set of common attributes? If you do the intersection schema, basically if you find the set of all common attributes, then that will be A. That's it. Okay, now what we will do? We want to check this attribute A, is this super key in R1 or R2? Okay, so what we will do, remember, in this set of given FDs, what we will do, we will find the closure of A, what A can determine. So you can see that A can derive ABC. That's it. You can easily see that A can derive ABC. So I can say that this A, this set of common attributes of R1, R2, this is a super key in R1. Okay, because you can see A can derive ABC. So that is the reason I can say that this R1 intersection R2, that is A, and that is a super key in R1. So this decomposition is lossless. Okay, what about this binary decomposition? R1 is ABC, R2 is CDE. So first you find what are the set of all common attributes. Okay, the common attribute is C. Now, in this given set of functional dependencies, you find what is the C closure. The C closure will be C only. So you can see that C is not a super key in R1, R2 both. C is not a super key in R1, C is not a super key in R2. So this decomposition is lossy, or I can say this decomposition is not lossless. Not lossless, that simply means lossy. So this decomposition is lossy. Let's solve this fourth book question. Suppose that we decompose the relation R into two sub-relations. Show that this decomposition is lossless decomposition if the following set of functional dependencies hold. Okay, so let's solve it. Very simple. This is a binary decomposition first of all. We are decomposing the original relation R into two sub-relations R1, R2. So this is a binary decomposition. And how to check if a binary decomposition is lossless or lossy? That is very easy. What we will do, we will find the set of all common attributes of the sub-relations. So what you do, you find what is R1 intersection R2, the schema intersection we are doing. So basically we are finding what are the set of all common attributes. So you can see that this attribute A, this is the common attribute. Only this attribute is the common attribute. So you can see that set of all common attributes, that is A. Now what we will check? We will check, is this a super key in R1 or R2? Means, can this determine all the attributes of R1 or can it determine all the attributes of R2? So for that what we will do? We will find what is the A closure, what A can determine, what A can derive. So you can see that A can derive ABC. That's it. So finally I can say that this decomposition, this is lossless. Why? Because here you can easily see that this A, which is R1 intersection R2, which is A, this is A. And remember, this can determine, this is a super key in the table R1. Okay, I can say this can derive all the attributes of R1. So that is the reason I can say that this decomposition is lossless. Okay, so the answer is yes, this decomposition is lossless. Okay, understood? The next topic is dependency preservation in a decomposition. So far we have seen what is lossy decomposition, lossless decomposition. Now the next important topic, that is dependency preservation in a decomposition. Is there any doubt so far? Rohit, let me know. Swaroop, Rohit, is there any doubt so far? Anyone has any doubt so far, or is everything clear? Let me know. So let's continue now. If there is any doubt, please put your doubt in the chat. I will see. Okay. Before we study dependency preservation in the decomposition, we need to study what is projection of functional dependencies. So this topic, projecting functional dependencies. So what is the meaning of projection of functional dependencies? Assume you have a relation R with set of functional dependencies F. Now let's assume that you take a subrelation of R. Let relation S contain subset of attributes of R. Means this relation S, this is a subrelation of R. Okay. Then we want to find out which functional dependencies will hold on the relation S. This is called projection of functional dependencies. Okay, so please understand that what this means. When I say projection of functional dependencies, what it means, you have original relation R, or I can say you have the database with set of functional dependencies F. So this relation R, this has FD set F. Okay, so these are the functional dependencies that hold on the relation R. Now what we are doing, we are taking subrelation of R. We are taking a subrelation of R. Okay, so let's assume that this S, this is subrelation of R, means basically all the attributes of S, those are in the R. Okay, so you can see the attributes of S, these are subset of attributes of R. So this is the subrelation of R. Now what we want to find out, we want to find out which functional dependencies will hold on S. Okay, so this is what we want to find out. We want to find out FD set of S. Okay, this is what we want to find out. Is this clear? This is called projection of functional dependencies. So you have original relation with set of functional dependencies. This is given to us. Now we are taking a subrelation of R. Basically, in this S, all the attributes, these are basically subset of attributes of R. Now we want to find out which functional dependencies will hold in this relation, in this subrelation S. Okay, this is what we need to find out. So you can see, assume we have a relation R with functional dependencies F. Now this relation S, this contains subset of attributes of R. Means this relation S, this is subrelation of R. We want to find out which functional dependencies will hold among the attributes of S. Which functional dependencies will hold in this relation, in this subrelation S. Okay. So basically we are projecting a set of functional dependencies onto a subset of attributes. Okay, so this is the idea. Basically we are projecting a set of functional dependencies onto a subset of attributes. Okay, for this subset of attributes we need to find out which functional dependencies will hold among these attributes. Okay, so let's see. Let's solve this York University question, projecting a set of functional dependencies onto a subset of attributes. Suppose that we have a relation R with attributes A, B, C, D, E, and these are the functional dependencies. Project the FDs onto attributes A, B, C. Okay, we need to find out which functional dependencies will hold between these attributes A, B, C. Okay, so please understand, the given functional dependencies, they hold in the database. Means among all the 5 attributes A, B, C, D, E, among these attributes, these functional dependencies they hold. But we are taking subset of attributes. We are taking a subrelation. Okay, now we want to find out which functional dependencies will hold among these attributes. Only among A, B, C, which functional dependencies will hold. This is what we want to find out. This is called projecting a set of functional dependency onto a subset of attributes. Okay, so we want to find out what is the projection of these FDs on these attributes. Okay, so very simple, you can see we want to find out which functional dependencies, which all functional dependencies will hold among the attributes A, B, C. And remember, this is very easy to find out. Always go in the step by step. Okay, I will tell you the procedure. Always follow this procedure if you don't want to mistake. Okay, if you don't follow this step by step procedure, then definitely in some question you will make mistake and you will lose marks. So just follow the step by step procedure that I am telling you. We want to find out which functional dependencies will hold among these attributes A, B, C. So how to find that? Very simple. What we will do, first we will start with what A can derive. Okay, let's see. In this set of functional dependencies, you find what is A closure. Basically what A can derive. And remember, our focus will be only on ABC, because we want to find out the functional dependencies that will hold among these attributes ABC. Okay, so first we will find out what A can derive. This is what we want to find out. Very simple point. I hope you understood. Okay, so in this set of functional dependencies, you find what is A plus. So if you find the A closure, that will be AC. We will also get ACE. You can see ACE. And from A, we can determine BD. So you can easily see that we got A determining BC. Okay, we got A determining BC. We don't have to write A determining A because that is trivial. We don't have to write trivial FD. So very simple point that A can determine BC. Remember, our focus is only on ABC. Okay, so you can see that A can determine here. In this, I can easily say that A can determine BC. Okay, so very simple. So you can see this functional dependency holds among these attributes ABC. Okay, then what we will do? Then we will find out what B can derive. Can B derive A comma C? Okay, so again what we will do? We will find B plus. So in this set of functional dependency, if you find B plus, that will be B only. So B cannot derive A or C. Okay, so you can forget about B. B cannot derive anything. Let's focus on C. What C can derive? So again here you find what is C plus. C plus will be CE, and you can see E can derive BD. So you can see CEBD. So please understand that C can derive B. Okay, yes or no? You can see C can derive B. So this functional dependency, this holds among these attributes ABC. C can derive B. Now this is fine. So now we have completed when LHS is having only one attribute. Okay, so these functional dependencies hold among these attributes. Now here you can notice one thing, that I can say among these attributes ABC, this A is a super key, this A is a candidate key, right? Okay, so now you don't have to check the superset of A, because if A is a candidate key, then its superset will also be a candidate. Its superset also will be a super key. If A is a super key, its superset also will be a super key. So we don't have to check the superset of A. Please understand. Now we don't have to check the superset of A. Now what we will do? We will check BC. Okay, let's see what BC can determine. Can they determine A? Okay, so if you find what is BC closure in this, if you find what is BC closure, then what that will be? That will be BC, BCE, BCED. Okay, so you can see they cannot determine A. So that also you can forget. Okay, so that's it. Finally, your answer will be A determines BC and C determines B. Okay, this will be your answer. Of course, if you want to minimize, you can do that. Okay, this answer is correct. Remember, this is the correct answer. If you want to minimize this, that also you can do. Okay, if you want to find the minimal FDs, then what that will be? You can see that A determines C and C determines B. Because remember, you can see that this A is determining BC, but remember A is determining C and C can determine B. So I can remove this A determining B, because ultimately you can see A determines B. So you can see this is the set of functional dependencies that hold among the attributes ABC. I hope you understood. You can read this explanation. Whatever I told you, that is written here. Let's solve this next question from the York University. We have a relation with 5 attributes A, B, C, D, E, and these are the functional dependencies. We want to find out which functional dependencies will hold among attributes A, D, E. Basically, we want to project the functional dependencies onto these attributes A, D, E. Okay. So let's see. Again, we want to find out which all functional dependencies will hold among the attributes A, D, E. And the step-by-step procedure I told you that you need to apply. Okay. So first what we will see? We will see what A can determine. Okay, can A determine D, E? So that is what we want to check. So in this set of functional dependency, you find what is A plus. So you can see the A closure, that will be AC. You can see C can derive E, and you can see E can derive BD. Okay, so very simple. Here you can easily see that A can derive DE. Yes or no? A can derive DE, because remember, focus on ADE. So you can easily see that A can derive DE. Okay, so that's it. So I can say this functional dependency holds among these attributes ADE. Okay, then what we will do? then we will find what D, because remember our focus is only on ADE. So let's see what D can derive. Okay, so here you find what is D plus. So the D plus, if you find, that will be only D. So there is no non-trivial FD. We will not get any non-trivial FD. You don't have to write the trivial FD. Okay, because trivial FD will always hold in every relation. You never have to write the trivial FD. They will always hold. Okay, so you can see that D cannot determine A, D cannot determine E. Okay, what about E? What E can determine? So again, very simple. In this, you will find what is E plus, what is E closer. You can see E closer will be EBD. E can determine EBD. That's it. So very simple point that E can determine D. Okay, these are the FDs we got. Now remember, you cannot stop here, because so far we have seen when LHS has only single attribute. What happens if LHS has two attributes? But remember, already you can see that A can determine every attribute of ADE. So I can say A is super key, and superset of super key is also super key. So you can see you don't have to check superset of A. You don't have to check when LHS has superset of A. That is what you don't have to check. Okay, but remember, you have to check what will be, what ED can determine. Can they determine E? Can they determine A? Okay, so in this also, again, what you will do, you will find what is ED closer. So remember, ED closer will be EDB. That's it. Okay, ED closer will be EDB. So you can see ED cannot determine A. So you can remove it here. And this is the set of functional dependencies you got. Okay, I hope you understood. Of course, if you want to minimize that, you can do. If you want to minimize, then what you can do, you can write it A determining E, E determining D. Okay, this is how you can write if you want to minimize. But remember, if you don't want to minimize, that is also fine. There is no necessity to minimize. If you do not minimize, that is also correct. This is also correct. If you want to minimize, that is also correct. So you can see that A can determine E, E can determine D. So transitively A can determine D also. Okay, so this is the set of functional dependencies that hold among these attributes ADE. So what is the procedure to find the projection of FDs on a subset of attributes? So very simple, go step by step. Okay, with LHS size 1, then 2, then 3, and so on. Okay, always go step by step. First you take size of LHS of FD equal to 1, then size of LHS 2, size of LHS 3, and so on. Only focus on finding the non-trivial functional dependency, because trivial functional dependency will always hold in every relation. So you only have to find the non-trivial functional dependency. And remember one thing, if LHS X is a key of S, okay, subrelation S, basically we want to focus on the subrelation S, because we want to find out which functional dependencies will hold on the subrelation S. Okay, so remember, if LHS is already a key, is already a super key, then we don't have to consider LHS which are superset of X. Okay, if something is already a super key, then we don't have to consider its superset, because its superset also will be a super key. So if LHS X is a key, then you don't have to consider those LHS which are superset of X. Okay, next, make sure that you don't miss any functional dependency that must hold in the relation S. Okay, so if you go in the step-by-step manner, then definitely you will not miss any functional dependency that should hold in the subrelation S. Okay, let's solve this question from the Ullmann book. You can see, suppose a relation R ABCD with functional dependencies. Suppose that we wish to project the attribute B out. Okay, basically we want to remove this attribute B. Okay, we only want to take ACD. Now the question is asking, in this R1, which functional dependencies will hold? Okay, we want to find out which functional dependencies will hold in the subrelation R1. I hope you understood the question. Remember, here in the question, a relation R ABCD is given to you. Okay, and for this relation R, the functional dependency set is also given to you. The FD set F is given to you. Now what we are doing? We are taking subset of attributes of R. Okay, we are taking a subrelation R1. We are taking subrelation of this relation R. So this subrelation we are taking subset of attributes of R we are taking. And now we want to find out which functional dependencies will hold in this relation R1. Find the functional dependencies for R1. Okay, So very simple. Now we want to find a FD set for R1, for this relation R1. Okay, so let's solve it. This is actually very easy. Already in this relation R ABCD, the functional dependencies, those are given to us. The functional dependencies are A determining B, B determining C, C determining D. Okay, and what we need to find out? We need to find out in this relation, in this sub-relation R1, which functional dependencies will hold. Okay, so these FDs we want to find out. So very simple. Remember what we will do? Go step by step. First you find what A can determine. Okay, so let's see what A can determine. So very simple here. Tell me what A can determine. You can see, you find the A closure. So if you find A closure, you can easily see that A can determine B, C, D. Okay, in this, if you find A closure, then that will be A, B, C, D. So you can see that A can determine C, D. Yes or no? A can determine C, D. Okay, what about C? What this can determine? You can easily see C can determine D. Okay, if you find the C closure, that will be CD. So C can determine D. Okay, what D can determine? Here if you find the D closure, that will be D only. So there is no non-trivial FD that we will get from D. Okay, this is when LHS has a single attribute. Okay, what happens if LHS has two attributes? Okay, after this you have to check if LHS has two attributes. But remember one thing, here you can see A is a super key because A can determine every attribute of ACD. So A is a super key. So now we don't have to consider when LHS is a superset of A. Okay, superset of super key is also super key. So now we don't have to consider those functional dependency where LHS is superset of A. Okay, so what we will consider? We will consider what about BC? Can BC determine A? So again here also what you do? You find what is BC closure. So the BC closure will be BCD. So you can see BC cannot determine A. So we will not get any non-trivial functional dependency when LHS is BC. Okay, so that's it. This is the answer we will get. I hope you understood. Of course, if you want to minimize that, you can do. Okay, if you want to minimize, then what we will get? We will get A determining C, C determining D. If you want to minimize, then this is what you will get. But remember, this is also correct answer. This is also correct answer. Okay. Very simple. So let's move on now. Let's solve this Ullmann book question. We have a relation R A B C D E with set of functional dependency. Okay, some set of functional dependency hold on this relation R. Now we want to project these functional dependency onto relation as ABC. Okay. Now the question is asking that for all these set of functional dependencies, you find which functional dependencies will hold on the subrelation S. Basically, among these attributes, which functional dependencies will hold? Okay, I hope you understood the question. Remember, we have a relation R. Now there are four questions. Okay, if you consider this is the set of functional dependency that hold on the relation R, then which functional dependency will hold on the subrelation S? This is what we need to find out. Similarly, if you assume that this is the set of functional dependency given for the relation R, then which functional dependencies will hold for the relation S? So basically, for the relation S, for this subrelation, we want to find which functional dependencies will hold among these attributes ABC. Okay, so let's solve it one by one. Let's solve this, that these are the functional dependencies that hold on the relation R. Now we want to find out which functional dependencies. Remember, we wish to project these functional dependency onto the relation R as ABC. Okay, so this is what we want to find out. We want to find out, give the functional dependency that hold in the relation S. If the FDs of R are given to you, these are the functional dependencies that hold on the relation R, and we want to find out which functional dependencies will hold on the relation S. Okay, so our subrelation S, that is ABC. So remember, to solve this question, always go in the step-by-step way. First, you consider when LHS has single attribute. Okay, so always focus on only these attributes, ABC. Only focus on these attributes. So let's see what A can determine. Okay, so what you will do, remember, in this given set of functional dependency, you will find what is A closure. Definitely A closure will be only A. Okay, so here if you see, then you will find that A closure, that will be only A. So we will not get any non-trivial functional dependency when A is on the LHS. Okay, next, What about B? What B can determine? So again here what you will do, you will find what is B plus. So you can see B plus also will be B. So when B is on the LHS, we will not get any non-trivial functional dependency. Okay, let's see what happens if LHS has C. What about C closure? So here if you find the C closure, that will be CE. You can see C can determine E, right? CE. And you can see E can determine A. So we got A also. Okay, CEA. This is what we got. So finally we got that C can determine A. Okay, remember this functional dependency will hold among these attributes ABC. So this is the first functional dependency that we got. Now what we will do? Now we will check when LHS has two attributes. Okay, when the size of LHS is 2. Okay, so let's see what AB can determine. Can AB determine C? Let's focus, because if I am taking the attribute AB on the LHS, then to create a non-trivial functional dependency, only attribute C is remaining. Okay, yes or no? So let's see, can AB determine C? Okay, so here also again what you will do, here you will find what is AB closure. So the AB closure, that will be AB, ABDE. Yes or no? Because AB can determine DE. So ABDE, and remember D can determine C. Okay, so what we got? Remember, we got that AB can determine C. So this functional dependency also we got. Okay. What about the next? What about the third one? For example, if your LHS is AC, then can we determine B? Can AC determine B? If you focus on the given set of functional dependency, then you can see no one can determine B except B. Only B can determine B. Okay, please focus on these set of functional dependency. Focus on these. Here you can see that no one can determine B. Only B can determine B. Only B can determine B. Yes or no? Because in the given set of functional dependencies, there is no functional dependency where on the RHS we have attribute B. This attribute B is not present on the RHS of any given functional dependency. So no attribute, no combination of attributes can determine B. Only B can determine B. Only B can determine B. So you can easily see that definitely AC cannot determine B. So you can forget about it. Or if you want, you can find what is AC closure, of course. Okay, let's find what is AC closure. So AC closure will be AC, ACE, because C can determine E. Okay, so ACE, that's it. So you can see AC cannot determine B. Okay, what about BC? What about BC? If LHS is BC, then you can easily see if C can determine A, then definitely BC can determine A. But you can notice C can determine A. So this is redundant. This functional dependency, this is redundant, right? Yes or no? I can say that this is redundant. Why this is redundant? Because already you can see that C can determine A. C can determine A, so automatically BC will determine A. So this is actually redundant. So you can forget about it. Your final answer will be C determines A and AB determines C. Okay, so for this first question, remember, for this first question, the functional dependencies, that will be your final answer. What will be your final answer for the first question? That will be these functional dependencies. That will be your answer. Okay, I hope you understood. Now, let's solve this question. Pause the video, try this question, which functional dependencies hold on the subrelation S, ABC, and write your answer in the comments. Then you play this video. Okay, so pause this video and please write your answer in the comments. Then you continue watching. So let's solve this question. These functional dependencies, they hold on the relation R, but we want to find out which functional dependencies will hold on the relation S. Okay, so you can see we want to give the functional dependency that hold on the relation S. So our relation S, that has subset of attributes. Okay, you can see this is the subrelation of R. So we want to find out which functional dependencies will hold in this subrelation S. So very simple, go step by step. You find what A can determine. Can A determine B, C? Can A determine B or C? So let's see. Okay, so here what you will do, here you will find what is A closure. What A can determine, you can see A can determine AD, because A can determine D, so AD. Okay, that's it, nothing else. So you can see that A cannot determine B or C. Okay, what about B? You can see that B closure will be B only. Okay, if you find what is B closure, that will be only B. So you can see B cannot determine A comma C. Okay, what about C? If you find the C closure, that will be C only. So C cannot determine A comma B. So when LHS is single attribute, then we will not get any non-trivial functional dependency. Okay. Now let's check when LHS has two attributes. For example, when LHS is like AB. Okay. And remember one more thing, you can notice a simple thing you can notice, that is, if you look at all these functional dependencies, then on the RHS, we do not have the attribute C. The attribute C is not present on the RHS of any given functional dependency. So only C can determine C. Yes or no? This simple observation you can make, that only C can determine C. Only C can determine C. So definitely AB cannot determine C. If you find the AB closure, you will see that AB closure will not contain C. So only C can determine C. Okay. So you don't have to take AB on the LHS because AB cannot determine C. Okay. Let's check what about BC. So you find what is BC closure. Okay. In this, let's find what is the BC closure. So the BC closure, what that will be? That will be BC only. So again, you can see that BC cannot determine A. Okay. The last thing, that is, let's check AC. Okay. What AC can determine? So here, what is the AC closure? AC closure will be ACD because A can determine D. So we got ACD. Next, remember, AC can determine E also. Okay. Now we got ACDE. Now remember, DE can determine B. DE can determine B. So that's it. We got that AC can determine B. This is the functional dependency. This is the only functional dependency that will hold in the relation S. Of course, all the trivial functional dependency will also hold on the relation S. Remember, trivial functional dependency, those will always hold in every relation, in every sub-relation. You never have to think about trivial functional dependency because trivial functional dependencies will always hold on every relation, on every sub-relation. So you can see that only this is the interesting functional dependency, or I can say only this is the non-trivial functional dependency that will hold in the sub-relation S. So this will be the answer. Okay. So far, is there any doubt? Please tell me, are you comfortable? So far, in every concept, are you comfortable? Let me know. Are you understanding each and every point that I am explaining? Please tell me. This projection of functional dependency, this is very important, let me tell you. Many students, they make mistake. In the GATE exam, if some nice question comes, then many students will make mistake in the projection of functional dependencies. And this is very useful in the dependency preservation. When we check if a decomposition is dependency preserving or not, then this concept is very important. So please understand this very clearly. That is the reason I am taking many examples. Let's solve this next question from the Ullmann book. So these functional dependencies are given to us, and these functional dependencies, they hold on the relation R. We want to find out which functional dependencies will hold on the relation S. On this sub-relation, which FDs will hold. Okay, so let's see. You can see this S, A, B, C. Now, there is a step-by-step procedure. What we will do? First, we will check if LHS has single attribute, then which functional dependencies we will get, which non-trivial functional dependency we will get. Okay, so let's see what A can determine. Can A determine B or C? The answer is no, because if you find what is A closure, that will be A only. Okay, so very simple point. In this here, if you find what is A closure, then that will be A only. So we will not get any non-trivial functional dependency when A is on the LHS. And what about B closure? What about B closure? So that will be B only. So when LHS has only attribute B, then we will not get any non-trivial functional dependency. What about C closure? That will be C only. So you can see that if LHS has single attribute, then we will not get any non-trivial functional dependency. Now let's try if LHS has two attributes. Okay. One thing you can easily notice in these functional dependencies, that attribute C does not appear on the RHS of any given functional dependency. So only attribute C can determine C. Yes or no? Only C can determine C. I hope you understood. So remember, AB cannot determine C, right? Yes or no? Okay, so you don't have to check when AB is on the LHS, because AB cannot determine C. Okay, let's check when AC is on the LHS, then what we will get. So you find the AC closure. Here, if I find what is the AC closure, what that will be? That will be ACE, because AC can determine E. So we got ACE. Remember E can determine B, so we got B also. Okay, we got B also. So we got ACEB. Now remember AB can determine D. Okay, notice here AB can determine B. AB can determine D. So we got all these. So I can say AC can determine B because we only care about ABC. We want to find out which functional dependencies will hold among these attributes ABC. So we will only focus on ABC. So you can see AB can determine, AC can determine B. Okay, what about BC? Very simple. You find what the BC closure, what BC can determine. So the BC closure, that will be BC. Okay, next BC closure. You can see BC can determine D. So we got D also. We got BCD. Okay, we got BCD. Next you can see D can determine A. So we got A also. We got ABCD. Okay, ABCD. That's it. So now you can see AC can determine E. So we got E also. So that's it. Finally, I can say that BC can determine A. Okay, so these are the functional dependencies that we got. This is your answer. Okay, is this clear? And remember, when LHS has 3 attribute, that we don't have to check, because if LHS has 3 attribute, then we will not get any non-trivial functional dependency, because this sub-relation, this has only 3 attributes. So if we put all the 3 attributes on the LHS, then we will not get any non-trivial functional dependency that hold among these attributes ABC. Let's solve this question from the Ullmann book. These functional dependencies hold on the relation R. We want to find out which functional dependencies hold on the relation S. Among these attributes ABC, which functional dependencies will hold? Okay, so you can see this S. These are the attributes ABC. So let's find out. Step by step procedure is there. First, what we will do? We will see what A can determine, what B can determine, what C can determine. Okay, you notice one thing here. In this set of functional dependency, you can easily see that A is determining B, B is determining C, C determines D, D determines E, E determines A. So actually, if you notice one thing, every attribute can determine every other attribute. See, there is a cycle here, like A can determine B, A determines B, B determines C, C determines D, D determines E, and E determines A. So if you notice these functional dependencies, that then every attribute determines every other attribute. Yes or no? Every attribute determines every other attribute. So now this question becomes very easy, because you can see that A will determine BC, B will determine AC, and C will determine AB. Okay, in simple words, I can write it that A will determine B, B will determine C, C will determine A. Okay, so this is the answer. Very simple. Okay, you can easily see A determines B, B determines C, C determines A. So this is the set of functional dependencies that will hold on the subrelation S. Among the attribute ABC, these are the functional dependencies that will hold. Okay, so we have studied and practiced. We have done a lot of practice of projection of functional dependencies on a smaller relation. I hope you are comfortable. Okay, let me know. Projection of functional dependencies, did you understand? On a subset of attributes, which functional dependencies will hold? Did you understand? Let me know. Okay, now let's move on now. Now the next topic, that is dependency preservation. Remember, so far we have already studied and we have done a lot of practice of projection of functional dependencies on smaller relations. Okay, on a subset of attributes, which functional dependencies will hold, that we have seen, and we have done a lot of practice. Now these concepts will be very important to study dependency preservation in a decomposition. A decomposition, when can I say a decomposition preserves functional dependencies? This is what we need to study. Okay, so let me tell you, we have a relation R. Okay, and in this relation R, we have some functional dependencies. Okay, so there is a FD set F. These are the functional dependencies that hold on the relation R. Now we are decomposing this relation R into sub-relations. Okay, let's assume that we are decomposing this relation R into R1, R2, R3. So these are the sub-relations of R. Okay, now you can easily see that this R1 contains subset of attributes of R. This R2 contains subset of attributes of R. This R3 contains subset of attributes of R. Okay, so some functional dependencies will hold on R1, some functional dependencies will hold on R2, and some functional dependencies will hold on R3. Yes or no? Okay, or I can say basically the projected FDs on R3, let's assume that is F3. Okay, let's assume the projected FDs on R3, that is F3. Let me call it F3. What this F3 means? This F3 means that these are the functional dependencies that hold on the relation R3. Means these are the functional dependencies that hold among the attributes of R3. Similarly, this R1 also has some functional dependencies that will hold on attributes of R1. So let me call that is F1. Okay, similarly this R2, this also has some set of functional dependencies that hold among the attributes of R2. Let me call it F2. Okay, very simple point. Now tell me one thing. A simple question I'm asking. When we are decomposing this relation R into R1, R2, R3, then some functional dependency. Okay, here we have all the functional dependencies of the relation R. Now, when we decompose this relation into sub-relations, then some functional dependencies will hold here, some functional dependencies will hold here, and some functional dependencies will hold here. Basically, some functional dependencies of F will hold here, some functional dependencies of F will hold here, and some functional dependencies of F will hold here. You tell me one thing. Is it possible that in this F1, F2, F3, we can get some functional dependency which is not present in this F? Let me know, is it possible? Is it possible that in the sub-relations, in this R1, R2, R3, in these sub-relations, can we get some functional dependency which is not present in the functional dependencies of the original relation R? Is it possible? Do you think? When we decompose a relation into sub-relations, can we get some additional functional dependency in these sub-relations? Is it possible? Of course, it is not possible. Yes or no? Because we are decomposing the original relation into sub-relations. So, some functional dependencies of F will hold in R1, some of F will hold in R2, some of F will hold in R3. We can never get a new functional dependency which is not present in F. Yes or no? So, I hope you understood the point. Now, I can say that maybe some functional dependencies can be lost. Remember, a new functional dependency we can never get, but maybe some functional dependency can be lost. Yes or no? Okay. So this is the point that, remember, if you find what is F1 union F2 union F3 closure, if you find the closure, then remember this closure will always be subset of F closure. Okay. But maybe it is possible that some functional dependency holds in this relation R, but it does not hold in these decomposed relations. That is possible. Okay, but remember, it is never possible that you will get a new functional dependency in the decomposed relations. So this is what I am telling you, that this will always happen. Okay, this will always happen. This equation will always happen. I hope you understood the idea. Okay, again I am telling you that this relation R we are decomposing into sub-relations. So it is never possible that a new functional dependency can hold in these sub-relations, which is not present in the original relation R. Okay, so new functional dependency you can never get. But maybe some functional dependency of R is lost in this decomposition. That is possible. Okay, when we do the decomposition, then maybe some functional dependency of the original relation can be lost. Okay, so remember, it will always happen that if you do F1 union F2 union F3, if you combine all these functional dependencies and then if you find the closure, that will always be subset of F closure. Okay, this will always happen. Now let me tell you, if they become equal, then we will say that functional dependencies are preserved. Okay, so remember, if they become equal means if this becomes equal, then I will say that functional dependencies are preserved. This is the case which is called, in this case I can say functional dependencies are preserved. Okay, FD preserved. FD is preserved. Okay, is this clear? Okay, basically no FD is lost. Okay, in this situation what we will say? In this situation we will say that no FD is lost in the decomposition. Is lost during decomposition, in the decomposition. Okay, no FD is lost in the decomposition. During decomposition, no FD is lost. Okay, and remember one more thing. If they are not equal, then we will say that some FD is lost in the decomposition. Okay, in this situation, we will say not dependency preserving decomposition. Not dependency preserving decomposition. Okay, in this situation we will say that some FDs are lost. In this case, what we will say that some FDs are lost. Some FDs are lost in decomposition. During decomposition, some FDs are lost. This is what we will say. I hope you understood the point. Okay, so again I am giving you the summary. We have a relation R with functional dependencies F. This is the FD set of the relation R. We are decomposing this relation R into subrelations. Then you can see that each subrelation will have some set of functional dependencies. Okay, for example, this F1, this is the functional dependencies that hold among the attributes of R1. F2 is the set of functional dependencies that hold among the attributes of R2, and F3 is the set of functional dependencies that hold among the attributes of R3. Okay, now remember one thing, that when we decompose a relation, then we can never get a new functional dependency in the decomposition. Yes or no? Of course, in the decomposition, a new functional dependency you can never get. But remember, it may be possible that some functional dependency of the original relation is lost in the decomposition. That may be possible. Okay, so here there are three cases. Again, I am telling you, here there are three cases. The first case that will always happen, that is, if you do the F1 union F2 union F3, if you combine all the functional dependencies of the decomposed relations, okay, if you do the union of all the functional dependencies, then you find the closure. Then remember, that will always be subset of F closure. This will always happen. Okay, this will always happen. Please understand, this equation is always true. This equation, that is always true. Is this point clear? This equation is always true. And remember, when this becomes equal, then we will say it is a dependency preserving decomposition. Means in the decomposition, no dependency is lost. And when this is not equal, then we will say that some dependency are lost. Or I can say this decomposition is not dependency preserving decomposition. I hope you understood the concept. Okay, so this is the summary. You can see that we have a relation R with the functional dependency set F, and we have a decomposition of this relation R into subrelations R1 to Rn. These are the subrelations. Now remember, this decomposition is dependency preserving. What it means? Dependency preserving decomposition. That simply means that no functional dependency is lost. Yes or no? No functional dependency is lost. So this decomposition is dependency preserving if and only if you do the union of F1, F2, F3, Fn, if you do the union of the functional dependencies of all the decomposed relations, that must cover F. Okay, please understand one thing, F will always cover F1 union F2 union Fn, right? Because I told you that, see, this equation is always true. What this equation means? If this equation is always true, what this means? This simply means that this F will always cover. This F always covers. This F always covers F1 union F2 union Fn. Yes or no? Okay, is this clear? This will always cover these. I hope you understood. Okay, this is the meaning, that this functional dependency set, this F, this will always cover these FDs. Now, if these FDs, means if you do the union of all these functional dependencies of the decomposed relations, if that can cover F, then we will say that this is a dependency preserving decomposition. Okay, so this is important point. You can notice that, see, if I say F covers these, that will always happen. Now, if these can cover F, then we will say that this is a dependency preserving decomposition. Okay, so very simple point. This decomposition is dependency preserving if and only if F1 union F2 union Fn. Okay, you take the union of functional dependencies of all the subrelations. So this F1 union F2 union Fn, this covers F. Okay, if this happens, then we will say that decomposition is dependency preserving decomposition. Okay, means every FD of F is inferred from F1 union F2 union Fn. This is the meaning of this statement, that F1 union Fn, that covers F. Okay, what it means? It simply means that every FD of F is inferred from this. Okay, let's move on now. Okay, and when can I say that decomposition is not dependency preserving? When can I say? We can say decomposition is not dependency preserving if and only if f1 union f2 union fn does not cover f. Okay, means there is at least one functional dependency of f which is not inferred from f1 union f2 union fn. Okay, this is the complete idea, this is the complete definition, this is what we have seen. Okay, so you can read this. A decomposition of a relation schema R into sub relations R1, R2, Rn is dependency preserving if all the FDs of R can be derived from the FDs of R1, R2, Rn. Okay, from the decomposed relations, if we can derive every FD of the original relation, then we can say that this decomposition is dependency preserving decomposition. Okay, so you can see that dependency preserving decomposition, then this equation must satisfy. Okay, f1 union f2 union fn whole closure is equal to f closure. This equation, if this equation satisfies, then we will say that decomposition is dependency preserving decomposition. Let's solve this question. A relation R ABC with functional dependencies is given to us. We break this relation R, we decompose this relation R into sub-relations R1, R2. Now we want to check, is this decomposition dependency preserving or not? Okay, so how to check it? It is actually very simple. Here first what you do, you find which functional dependencies will hold in R1, which functional dependencies will hold in R2. Okay, so this is what you need to find, remember. So already you can see that this relation R has FD set F. Okay, we need to find which functional dependencies will hold in R1. So we have to find the FD set F1, means the projected FDs on R1. Okay, which of these FDs are projected on R1? Okay, similarly for R2 also we need to find what is the FD set R2, F2. Basically, which FDs will hold among the attributes AC. Okay, so this is what we need to find. So first we will find what is F1. Okay, so let's see. Can A determine B? Yes, A can determine B. Yes or no? So definitely in this F1 we will get A determining B. Okay, what about B determine A? Can B determine A? You can easily see no, B cannot determine A. So this is F1. Means in this relation R1 only this functional dependency will hold. Okay, among the attributes AB only this functional dependency will hold. Now let's find out what is F2. Which FDs will hold among the attributes AC? Can A determine C? Yes, A can determine C, because remember, A can determine B, B can determine C. Yes, A can determine C. So A can determine C. Can C determine A? No, C cannot determine A. If you find C closure, that will be C only. So C cannot determine A. So you can see this is F1, this is F2. Now, understand one thing very carefully. We know that what is always true. See, what always happens. What always happens. What always happens. Remember, what will always happen? Always. You don't even have to check. What will always happen? It will always happen that this F will cover F1 union F2. Okay. So what will always happen that F covers, okay, the FDs of the original relation, they will cover F1 union F2. Here actually you can easily see that this F, this actually covers F1 union F2. You can see this FD is covered in F. This FD is covered in F. Okay, so both these FDs, they are covered in the FD set F. So you can see F covers F1 union F2. This will always happen, notice. You don't even have to check. This will always happen that F covers F1 union F2. Okay, this same statement I can write in another way. I can write in another way that this will always happen that F closure will be superset of F1 union F2 closure. This will always happen. Okay, you don't have to check. Now what we have to check for dependency preservation? For dependency preservation we have to check, does F1 union F2 cover F? This is what we need to check. Okay, basically we need to check, does F1 union F2 cover F? Does it cover F? This is what we need to check. Okay, so let's see. You check this F1 union F2. First of all, what is F1 union F2? Okay, in this F1 union F2 we have A determining B. Also we have A determining C. So now you tell me, does it cover F? Can I say every FD of F is inferred from F1 union F2? The answer is no. You can see this FD is covered. Okay, F1 union F2 infers this functional dependency A determining B. So this functional dependency is covered by F1 union F2. Okay, you can easily see that A determining C. This FD is also covered by F1 union F2. But what about this functional dependency? This functional dependency is not covered by F1 union F2. In this F1 union F2, if you find B plus, what that will be? That will be B only. So you can see that F1 union F2 does not cover B determining C. So this FD is lost. Please understand, this FD is lost in decomposition. This FD is lost in decomposition. So this decomposition is not dependency preserving decomposition. Is this point clear? This FD is lost in the decomposition. So this decomposition is non-dependency preserving decomposition. Okay. Let's move on. Let's see this example. Is this decomposition dependency preserving or not? Again, very simple point. You can see this relation has FD set F. Okay, these are the FDs that hold in the relation R. Now, first what we have to find? We have to find which FDs will hold in R2 and which FDs will hold in R1. Yes or no? So, what you do? You find what is F1. F1 means which FDs will hold in R1. So let's see, can A determine B? Yes, A can determine B. You can easily see A determines B. Can B determine A? No, B does not determine A. So this is F1. These are the FDs that hold in the relation R1. Okay, let's see what is F2. Can B determine C? Yes, B determines C. Can C determine B? No, C cannot determine B. So you can see these are the FDs that hold in R2. Okay, now remember, F will always cover F1 union F2. That will always happen. You don't have to check. Okay, this original relation functional dependency F, this FD set F, this will always cover F1 union F2. Okay, you don't have to check. But what we have to check for dependency preservation? We have to check, does F1 union F2 cover F? Okay, so this is what we need to check. Does F1 union F2 cover F? Okay, so let's see. First of all, you write what is F1 union F2. What is that? Union of F1 comma F2, that will be A determining B, B determining C. This is the union of F1 comma F2. Now let's see. Does F1 union F2 cover F? Okay, let's see. Every FD of F can be covered by F1 union F2 or not. Okay, let's check this FD. Is this covered? This functional dependency, is this covered by F1 union F2? Yes, this FD is covered. Okay, this FD is covered, you can see. So F1 union F2 covers this FD, that is fine. What about this B determining C? Yes, this is also covered by F1 union F2. What about this A determining C? That is also covered. This is also covered. Why? Because in this F1 union F2, if you find what is A plus, that will be ABC. So you can see that A determines C, that is also covered. So I can say that every FD of F is covered by F1 union F2. So this decomposition is dependency preserving decomposition. Okay, so you can see the answer is yes. Does F1 union F2 cover F? The answer is yes. Okay, so remember, this decomposition is dependency preserving decomposition. I hope you understood. Let's solve this question. Is this decomposition dependency preserving or not? A relation R with functional dependencies F. We are decomposing this relation R into R1 comma R2. Now we want to check, in this decomposition, do we lose any dependency or not? Is this decomposition dependency preserving or not? So what is the method? Very simple. See, in this relation R, the functional dependencies that hold, that is F. Okay, for this relation R, the FD set is F. First, what we have to find? We have to find which FDs will hold on R2, which FDs will hold on R1. Okay, so we have to find what is the FD set of R2, that means F2. And we also have to find which FDs will hold on R1. Okay, we also have to find which FDs will hold on R1. So FD set of R1, that is F1, we have to find, and we have to find F2. So first we will find F1, F2, then we will solve this question. So first let's focus on F1. Okay, what FDs will hold among these attributes ABC? So you can easily see that what A can determine. Yes, A can determine BC. So this FD will hold in the relation R1. In the relation R1, A determining BC, that will hold. Okay, what about B? Can B determine A comma C? No, B cannot determine A comma C. You can find the B closure that will not contain B, A comma C. Okay, what about C? Can C determine A comma B? No. You can find C closure that will not contain A comma B. Okay. Okay, and you can see that here in this relation R1, you can easily see that this A is super key. So you don't have to check those FDs where LHS is superset of A. Because A is already super key, superset of a super key is already a super key. So we don't have to check those FDs where LHS is superset of A. Okay, so let's check what about BC. Can BC determine A? So you find what the BC closure. Okay, let me find what is BC closure. So if you find the BC closure, that will be BC. B can determine D. You can see B can determine D. So BC closure will be BCD. You can see CD can determine A. CD can determine E. We got E also. You can see E can determine A. So we got A also. So very simple. BC can determine A. This is the FD we got. So that's it. Finally, I can say this is the F1. Okay, we got F1. Means these are the FDs that hold on relation R1. Okay, let's find out F2 now. Which FDs will hold in the relation R2? Okay, so let's see again A. Can A determine DE? You can see, find the A closure. A closure will be A, B, C. B can determine D. Okay, and you can see CD can determine E. So yes, A will determine DE. You can easily find, here you can easily find what is A closure. Okay, if you find the A closure, in this, if you find the A closure, let me write it here. Here, if you find the A closure, what that will be? You can see A closure will be ABC. A can determine BC. Next, you can see B can determine D. We got D also. You can see CD can determine E. This CD, this can determine E. So that's it. You can easily see that A can determine DE. We got D. Okay, what about D closure? You can see D cannot determine A comma E. D closure will be D only. What about E closure? E closure, you can see E can determine A. Yes or no? E can determine A. You can easily see, if you find the E closure, that will contain D also. Okay, that will contain D also, right? If you find the E closure, let's find here. If you find what is E closures, you can see E will determine A. Now remember, A can determine everything. Okay, you already know that A closure contains every attribute. So E can determine A can determine everything. So I can say E can also determine everything. So we got everything. So that's it. So finally I can say these FDs hold in the relation R2. So we got F1, F2. Okay, let me write it here. We got F1. Now you find what is F1 union F2, right? Okay, for dependency preserving decomposition, you need to check, does F1 union F2 cover F? So now F1 union F2. What is F1 union F2? That is A determining BC, BC determining A. Next, A determining DE. Okay, next, E determining AD. Okay, is this clear? So very simple. Now let's see. Now what you check? You check, does F1 union F2 cover F? Okay, this is what we need to find out. Does F1 union F2, does it cover F? Okay, so let's see. F1 union F2, does it cover every FD of F? For example, A determining BC. Is this FD covered? Yes, this FD is covered. You can see. So this A determining BC, this FD, this is covered by F1 union F2. What about CD determining E? So here you find what is CD plus. You find what is CD closure. In this F1 union F2, you find CD closure. That will be CD. Okay, that will be CD. That's it. So CD does not determine E. This FD is lost. Yes or no? Notice one thing. This FD is lost in the decomposition. Did you understand? Please tell me. This CD determining E. This FD we have lost. Lost in decomposition. Okay, is this point clear? So this decomposition is not dependency preserving decomposition. Is the decomposition dependency preserving? The answer is no. Okay, so you can see, does F1 union F2 cover F? The answer is no. Let's move on now. So I hope you understood. So let's see this. This is the conclusion. Relation R with FD set F. we have a decomposition. We are decomposing this relation R into sub-relations R1 to Rn. Now, we already know that this F, this will always cover F1 union F2 union Fn. Okay, this will always happen, right? We have already seen this, that F will always cover the functional dependencies of the original relation. You can see this FD set F, this will always cover F1 union F2 union Fn. Okay, this will always happen. So basically it simply means that this F closure, this will be a superset of, F1 union F2 union Fn closure. Union Fn closure. Okay, so this equation will always be true. Okay, let's see the next. So you can see you have a relation R with the FD set F and you have this decomposition. Okay, so let's assume that this R1 has FD set F1, this R2 has FD set F2, R3 has FD set F3, and this Rn has FD set Fn. Okay, so these are the FD sets of the decomposed relations. Then here remember there are three things. What is the first thing? First thing is what always happens. So what always happens? It always happens that if you do the union F1 union F2 union Fn, if you do the union closure, that will always be subset of F closure. This will always happen. The second thing, what is the definition of dependency preservation? When can I say dependencies are preserved? Dependencies are preserved. So when can I say dependencies are preserved? Dependencies will be preserved if this equation becomes equal. Okay, if this becomes equal means F1 union F2 union Fn, if this whole closure, if this becomes equal to F closure, then we will say that the dependencies are preserved. Okay, and when can I say dependencies are not preserved? When can I say dependencies are not preserved, or I can say some dependencies are lost? So when can I say that this decomposition is not dependency preserving? When this equation becomes not equal, means this F1 union F2, okay, union Fn, this whole closure, this is a proper subset of F plus. Okay, this is proper subset of F plus. Remember, proper subset of F plus. Okay, so this is the idea. Now let's move on. So please tell me, so far everything is clear? Let me know. Each and every point is clear or not? Let me know. अभी तक सब कुछ समझ में आया? Projection of FDs, lossless, dependency preservation, how to check, okay, every concept. And we have done practice also. Enough practice also we have done. Let me know. Nishant, thank you Nishant, thank you so much. Rohit is asking, why do we want to preserve the functional dependencies? I mean, why not? Functional dependencies, these are the constraint on the database. The database owner, the database designer, they are putting some condition on the database that, for example, I want that roll number should determine the name. This is the condition I want in my database. Okay. If I am the school principal, I want to create a database for my school. I want this condition that roll number should determine the name. If I know the roll number, then I should be able to determine the name, right? Yes or no? Now you tell me, would you like to lose this dependency? So of course, dependency preservation is definitely a very desirable thing. Yes or no? We want to preserve the dependencies. That is a desirable thing. Why do you want to lose dependencies? Okay. In my school database, I want that passport number, okay, passport number or maybe Aadhaar card number, that should be able to determine the person uniquely. Yes or no? From the Aadhaar card number, I should be able to determine the name. So, would you like to lose this dependency? No, of course not. Yes or no? For example, in the national database, okay, in our country India database, we want that district should determine state. Okay, if you know the name of the district, then definitely you should know the name of the state. Okay, have you seen this? Whenever you are filling the gate application form, and let's assume there is a district column and there is a state column. Have you seen this, that when you fill the district, then automatically state column will be filled? You don't have to fill it. Okay, in the district column, as soon as you put Jaipur, you just put Jaipur, automatically Rajasthan will come here, because there is a functional dependency that district determines state. So when you put Jaipur, then automatically this Rajasthan will come. Okay, so this functional dependency we want to preserve, we don't want to lose it. So very simple point, that dependency preservation is a desirable thing. We don't want to lose dependency. It is a obvious and desirable thing. I hope you understood. Let's move on now. Now we will study how to check lossless or lossy for non-binary decomposition. So far we have seen that if you have a binary decomposition, then we can very easily check whether the decomposition is lossless or lossy. And what the procedure? You can see, for a binary decomposition, where when we are decomposing a relation into two sub-relations, then this decomposition will be lossless if and only if the set of all common attributes of R1, R2 is a super key in either R1 or R2 or both. Okay, this we have already seen that when you have a binary decomposition, then when can I say this decomposition is lossless? This binary decomposition will be lossless if and only if when I find the set of common attributes of R1, R2, means R1 intersection R2, the schema intersection, we are finding the common attributes of R1, R2. This set of all common attributes of R1, R2, this must be a super key in R1 or R2. So you can see this must be able to determine R1 or this must be able to determine R2. In this situation, we will say that our decomposition is lossless, otherwise our decomposition will be lossy. Okay, otherwise we will say that our decomposition is lossy. So this is the idea, this is the method to find whether a binary decomposition is lossless or lossy. But how to find if a non-binary decomposition is lossless or lossy? Okay, how to check if a non-binary decomposition is lossless or lossy? Okay, so for that, the answer is chase test. Okay, so remember, whenever in the gate exam, in any question, if a non-binary decomposition is given to you, means we are decomposing a relation into three or more sub-relations. First of all, you understand what the meaning of non-binary decomposition. Okay, so let me explain this point. Non-binary decomposition. So this non-binary decomposition, this simply means that we are decomposing our relation into three or more sub-relations. Okay, is this clear? We are decomposing our relation into three or more sub-relations. Three or more sub-relations. I can say three or more sub-relations. Okay, is this point clear? Very simple point. I hope you understood. So this is called non-binary decomposition. Remember, for binary decomposition, there is a straightforward method. Okay, if you have a binary decomposition and you want to check whether this is lossless or lossy, then this is actually very simple. You just find the set of all common attributes that must be a super key in at least one of these decomposed relations. Okay, this is the method for binary decomposition, lossless or lossy checking. Okay, but how to check if non-binary decomposition is lossless or lossy? So if we decompose a relation into three or more sub-relations, then how to check whether this decomposition is lossless or lossy? For that, the answer is the chase test. And this is very easy and very interesting and very efficient. Okay, let me tell you that some students, I have seen some students and some coaching teachers also, they apply successive combining method to check whether a decomposition, whether a non-binary decomposition is lossless or lossy. Some students and some teachers, what they do, they apply successively combining method. Okay, and let me tell you, this is a wrong method and this is a misconception. This is a major misconception. So this is what I'm telling you. Actually, maybe you have seen this, that whenever there is a non-binary decomposition, like we are decomposing this relation R into R1, R2, R3, R4, like that. Okay, then how to check whether this decomposition is lossless or lossy? Then some students, what they do, some teachers, what they do, they successively combine two sub-relations. Like for example, what they will do, they will combine these two, then they will combine these two, then they will combine these two, then they will combine these. So like that, basically they will successively combine two relations. Okay, you can read this here. Successively combine two relations. This method they will apply. And let me tell you, this method is wrong first of all. Okay, this is a wrong method and this is a major misconception. So please don't do that. Okay, please don't take successively two relations and then you are merging them. Please don't do that. This is a misconception. This is a wrong method. So what is the correct method? The correct method is chase test. And let me tell you, this chase test is not only correct method. This is easy method and efficient method. This will save a lot of time. In the gate exam, if let's assume there are 5 sub relations, we are decomposing our relation into 5 or 6 or 7 sub relations. Then let me tell you, chase test takes least amount of time. Okay, chase test is easy, it is efficient, and it is correct. Okay, so let's study the chase test now. So now we are going to study the chase test to check if a decomposition is lossless or lossy. And let me tell you one interesting thing about chase test. This is applicable for binary decomposition, also for non-binary decomposition. Okay, but remember, for binary decomposition you don't have to apply the chase test because there is already a very simple condition, right? Okay, so for binary decomposition, if you want to check whether it is lossless or lossy, then what you can do, you can just simply find the set of common attributes that must be a superkey in at least one of the decomposed relations. In this situation, we will say that decomposition is lossless, otherwise the decomposition is lossy. Okay, but remember, this chase test actually, technically I can say, you can apply this for binary decomposition also, you can apply this for non-binary decomposition also. So this chase test works for every type of decomposition. Okay, so let's study the chase test to check if a decomposition binary or non-binary, binary or non-binary. Okay, if a decomposition is lossless or lossy. So let's see this. So this is the chase test, or I can say this is the chase algorithm. Okay, it looks complicated, but actually this is very simple. Okay, so let's try to understand this. We will make it more simpler, let me tell you. Okay, it is just looking complicated, but it is actually very simple, and we will make it even more simpler. So with the help of example, we will try to understand this. So let's consider this example. We have a relation R which has 5 attributes D, E, F, G, H, and some set of functional dependencies. Okay, and we have a decomposition of R into 4 sub-relations R1, R2, R3, R4. You can see R1 has attribute DE, R2 DF, R3 EFG, and R4 that is DGH. Okay, so this is the decomposition of the relation R into 4 sub-relations. We want to check if this decomposition is lossless or lossy. First of all, you can see this is a non-binary decomposition. We are decomposing our relation into more than two sub-relations. So this is the non-binary decomposition. For non-binary decomposition, always apply the chase test. Okay, so let's see whether this decomposition is lossless or lossy. How to check using chase test? Let's understand the chase test now. Okay, let me tell you the step 1 of the chase test. So the step 1 in the chase test, what we do, the step 1, that is we create a matrix. Okay, in this matrix, remember, the columns are the attributes and the rows are the sub-relations. Okay, so let me tell you the step 1 of the chase test. So the step 1 is we create a matrix. Okay, in this, what we will do, we will create a matrix where the columns will be attributes. Okay, is this clear? You can see that our columns, what are the attributes? You can see our relation has attribute D, E, F, G, H. So there are 5 attributes. So you can see D, these are the attributes. So we will write the attributes here, D, E, F, G, H. Okay, is this point clear? We will write the attributes here. Okay, so on the columns we are writing attributes, and remember on the rows we will write the sub-relations. So how many sub-relations are there? There are 4 sub-relations, R1, R2, R3, R4. Okay, so here I will write R1, R2, R3, R4. Okay, now what the next thing? The next thing is the step number 2. Okay, this is the step number 1, let me tell you. Now let's see the step number 2. The step number 2. Step number 2 is, you can read here that step number 2, that is for each sub-relation under its attribute you put A entries. Actually these A entries we will put, and these are very important. Okay, I will tell you how. So basically for each sub-relation, basically in every row under its attributes you put A entries. Okay, for every sub-relation, for this relation R1, under the attributes of R1 we put A entries. For this relation R2, under the attributes of R2 we put A entries. Similarly, in this relation, in this row, for this relation R4, under the attributes of R4 we put A entries. Okay, so you can easily see that the attributes of R1, those are DE. Okay, so you can see those are DE. So here I will put this entry A, and here also I will put entry A, because the attributes of R1, those are DE. Okay, so that is the reason here I am putting the entry A. Okay, let's see the next. That is, in R2 we have attribute df. Okay, so in this R2 the attributes are df, so we will put entry a under d comma f because these are the attributes of R2. Okay, next the attributes of R3, these are efg. So under efg for this R3 we will put a entries. Okay, so we will put a entries like this. Okay, like this. So these are the rows. Okay, next you can see for this R4 dgh, these are the attributes of R4. So under dgh we will put a entries, dgh. Okay, this is what we got. Okay, understood? So this is the step number 2. I hope you understood. Now let's see the step number 3. Let's see here. You can see step number 3, that is we repeatedly apply the functional dependencies on the matrix. This matrix that we got, on this matrix we will repeatedly apply the functional dependencies. Okay, functional dependencies will be given to you. Now what we will do, the step number 3, we will apply the functional dependencies. Okay, apply, this is the apply fds on this matrix. Okay, on this matrix what we will do, we will apply the functional dependencies. Now what it means, apply the functional dependencies, what it means? So let me explain. It is very simple. For example, let's assume there is a fd. Assume there is a fd. Okay, let's assume there is a given fd, and this given fd is, let's assume d determines e. This is the given fd, d determines e. Okay, this fd is given to you in the question. This fd is given to you. This is the given fd, d determines e. First of all, you tell me what this fd actually means. When a functional dependency is given to you, d determines e, what this actually means? See, it simply means that whenever two tuples have same d value, then they must have same e value. Yes or no? Very simple point, that whenever two tuples will have same d value, then they must have same e value. This is the definition of functional dependency. Okay, so you tell me one thing. Let's assume that these tuples, okay, like let's assume that these tuples have d value 4, 4, 4. Okay, and let's assume this tuple here, we know that e value is 5. Then can you tell me what will be the value of e here, here, and here? Can you tell me? Very simple point. Functional dependency definition, what it says, d determines e. What it means? It means if two tuples have same d value, then they must have same e value. So you can see, if I tell you that in this here, you know that here the d value is 4, e value is 5, then automatically what will happen? That whenever d value is 4, then e value must be 5. Yes or no? So automatically this value will be 5, this value will be 5, this value will be 5. Okay, so this is what I'm saying, that you apply the functional dependency. I told you, apply functional dependencies on this matrix. So you can see d determining e. What it simply means? It simply means that if you know that if the d value is 4 and e value is 5, then automatically what will happen? Whenever d value will be 4, then e value automatically will be 5. This is what it means. I hope you understood. Okay, so just apply the functional dependency now. So here you can easily see that in these three, okay, look, see, in the column of d, here you can see the value of d is equal to a. Okay, now you can easily see here value of d is a, value of e is a. Okay, so automatically what should happen? Here also the value of e should be a, here also the value of e should be a. Do you agree with me? Okay, very simple point I am saying that. Look at these three tuples. Okay, under the column d. So here the d value is a. Okay, d determines e. This functional dependency is given to us. So whenever two tuples have same d value, they must have same e value. Okay, so you can easily see that for these tuples, for these three, the e value must be same. Now it is already a. This value of e is already a. So automatically this value also will be a. This value also will be a. Okay, so like this you can apply the FD. This is what I'm saying, that apply the functional dependencies in the matrix. Okay, understood? Now let's assume that another functional dependency is given to you. Okay, so let's assume that one more functional dependency is given to you in the question, and that is like DE determining H. Okay, this functional dependency is given to you, D determining H. Then tell me, in this situation what we will do? Again, very simple, D determining H, it simply means that if two tuples have same D value, then they must have same H value. Okay, if two tuples have same DE value, for example, here you can see that these, look at this tuple, look at this tuple, look at this tuple. They have same DE value, here also A, here also A, here also AA. So you can see these tuples have same DE value. So they must have same H value. Do you agree with me? These three tuples must have same H value. Okay, so what we are going to do? We are going to put these tuples must have same H value. Already this H value is A. So here also I should put A. Here also I should put A. Okay, so this is what I'm going to do. Here I will put A. Here I will put A, like this. I hope you understood. Okay, very simple point, right? Now, let's assume another functional dependency is given to you, and that is the another functional dependency is, let's assume, that is FG determines H. Okay, let's assume this is given to you. FG determines H. Okay, let's assume this FD is also given to you. FG determines H. Then what it actually means? This means that whenever two tuples have same FG value, then they must have same H value. Agree with me? Whenever two tuples have same FG value, then they must have same H value. Now you look at, is there any two tuples which have same FG value? Okay, remember one thing. These empty cells, okay, these value we don't know. They may be equal to A, they may be different from A, we don't know. Please understand. These empty cells, the value is unknown. You cannot consider is A. The value is unknown value. Okay, it may be same as A, it may be different from A, I don't know. The point is, these are unknown values. These empty cells, all these empty cells. Okay, this empty cell, this is also unknown value. Okay, is this clear? Now you notice this FD is given to us, FG determining H. So whenever two tuples have same FG value, then they must have same H value. But you can notice that no two tuples have same FG value. Okay, here we don't know what is the FG value. Here FG value is A, unknown. Here double A, here unknown, A. So in this situation, right now this FD is not useful for us. Okay, maybe after some time we can use it, but right now this FD we cannot use. Right now we cannot apply this FD. Okay, maybe after some time we can apply this FD. Okay, so I hope this point is clear. Okay, understood? Let me know. So this is how you can apply the chase test. Okay, is this clear? So you can easily see that in the chase test, remember the step number 1, that is create the matrix where the columns are the attributes and the rows are the subrelations. Then the step number 2, for every subrelation under its attribute you put A entries. Then the step number 3, you repeatedly again and again, okay, repeatedly apply the functional dependencies in the matrix. Okay, then the step number 4, if you get, please understand, if we get some row, if we get some tuple where all the entries are A, if we get this type of tuple, if we get this type of row where every entry is A, okay, all the entries are A, then you can stop and you can say that decomposition is lossless. Okay, else the step number 5, if there is no row with all entries A, if there is no tuple where all the entries are A, and no more changes you can do in the table, because remember you apply the functional dependencies repeatedly, again and again you apply the functional dependencies. But if you cannot do any more changes in the table, no more changes can happen in the table, then you can stop and you can say lossy. Okay, so when can you say lossless? If you get some tuple, some row, at least one tuple, at least one row with all entries A, then you can stop and you can say lossless. And if there is no tuple with all entries A and no more changes you can do in the matrix, then you can stop and you can say that the decomposition is lossy. So this is the chase test. Okay, and let me tell you, this is very easy to apply and very interesting also. We will do a lot of practice, don't worry. So let's start now. Let's solve this question. Consider the relation R, A, B, C, D, and this is the decomposition. Okay, and these are the functional dependencies. This decomposition is lossless or lossy. First of all, you can notice that this is non-binary decomposition. Yes or no? We are decomposing relation R into 3 sub-relations R1, R2, R3. So because this is a non-binary decomposition, then we must apply the chase test to check whether this decomposition is lossless or lossy. Yes or no? Okay, so let's apply the chase test now. What is the step number 1? You create a matrix. Okay, so let's see the step number 1. The step number 1 is we create matrix where the columns are the attributes. Okay, how many attributes are there? There are total 4 attributes. So these are the columns. Okay, in the columns I will write the attributes A, B, C, D. These are the attributes. Okay, next, In the rows, what I will write? Columns are the attributes and the rows, those are subrelations. Okay, so how many subrelations? There are 3 subrelations. We are decomposing R into 3 subrelations, R1, R2, R3. So this is the step number 1, that we create a matrix where the columns are attributes and the rows are the subrelations. Now what the step number 2? The step number 2 is, for every subrelation under its attribute we put A entries. So you can see R1 has attribute AB, I will put A entry. R2 has attribute BC, I will put A entry here. R3 has attribute CD, I will put A entry here. Okay, very simple. So this is the step number 1, step number 2. Okay, we have created the matrix and you can see for every subrelation under its attribute we have put the A entry. Now what the step number 3? Now we will apply the functional dependencies. Yes or no? So remember, this is the step number 1 and 2. Step 1 and 2 we have done. Okay, now let's focus on the step number 3. That is, we will apply the functional dependency. Okay, this is the step number 3. This is the step number 3. That is, apply functional dependencies repeatedly. Apply FDs on this table, on this matrix. Okay, on this matrix, what we are going to do? We are going to apply the functional dependencies. Okay, so let's see which functional dependency we can apply. So you can see that A determining B. So whenever 2 tuples have same A value, they must have same B value. But you can see right now no 2 tuples have same A value. Yes or no? Remember, these values, these empty cells, these are unknown values. We don't know. They may be equal to A, they may be different from A, I don't know. So please understand, right now at this moment in this column A, there is no 2 tuples which have same A value. Okay, because this is unknown value, this is unknown value, we don't know what the value here. They may be same as A, they may be different, they may be anything. Okay, so you can see this FD we cannot apply right now. Okay, what about this B determining C? Yes, I can apply this FD, right? Okay, because you can see whenever 2 tuples have same B value, they must have same C value. You can see these 2 tuples have same B value, so these 2 tuples must have same C value. Already C value here is A, so this C value also must be A. So that's it. So we will put A here. Okay, so this FD we are applying. Next, what else we can do? Let's apply this FD, C determining D. What it means? It means that whenever 2 tuples have same C value, they must have same D value. You can see these 3 tuples, all the 3 tuples have same C value, then they must have same D value. These 3 tuples, they must have same D value. Already this value A is here. So what I will do? I will put this A value here also, here also. Okay, here also, here also. So I hope you understood. Okay, is this clear? Please tell me. So like this you can do. Okay. So like this we can do. So that's it. So finally, now you can stop. Why you can stop? Tell me. Because look at this row. This row has all the entries A. Okay, look at this tuple. This tuple has all entries equal to A. Okay, so let's focus on this tuple. So here you can see every entry is A. Here all entries are A. And because all entries are A, so now you can stop. Okay, now you can stop and you can say that this decomposition is lossless. Okay, now you can stop. Now you can stop and you can say that this decomposition is lossless. Isn't it simple? Let me tell you, this chess test will become your favorite. Okay, it will become your favorite. It is so interesting and so easy. In the GATE exam, if they give you, let's assume 7 subrelations, R1 to R7, we are decomposing our relation into 7 subrelations. Then also, if you want to check whether the decomposition is lossless or lossy, this chess test is so easy. Within 30 seconds, you can solve the question. Okay, so chess test is the correct method. Also, it is the easy and efficient method. Also, this is very interesting method. Okay, so here the answer will be lossless because there is at least one tuple. We got at least one tuple where all the entries are A. So you can stop and you can say that this decomposition is lossless. Let's move on. So remember this chess test we have already seen. Okay, let me again repeat the steps of the chess test. The step number 1, that is create a matrix where the columns are attributes and rows are the subrelations. The step number 2, for every subrelation under its attributes, we will put the A entries. Then the step number 3, we will repeatedly apply the functional dependencies in the matrix. Then the step number 4, if we get some tuple, some row with all entries A, then we can stop and we can say lossless. And the step number 5, if there is no row with all entries A and no more changes you can do in the matrix, then you can stop and you can say lossy. Okay, let's solve this question from the Ullmann book. Let's read this question. Relation R A B C D E. This is decomposed into relations, sub-relations, three sub-relations. So this is not a binary decomposition. Yes or no? We are decomposing our relation into three sub-relations. So this is non-binary decomposition. For each of the following FD set, like this FD set is given to you, we have to use the Chase test. The Ullmann book is saying that use the Chase test to tell whether the decomposition is lossy or lossless. Whether the decomposition of R is lossless or lossy. Okay, so this is what we need to do. We need to apply the Chase test to check whether this non-binary decomposition is lossless or lossy. So let's solve it. I told you how to apply the Chase test. The step number 1, that is matrix. Create a matrix where the columns are the attributes and the rows are the sub-relations. Okay, so let's see how many attributes are there. A, B, C, D, E. 5 attributes are there. So let me create like this. Okay, so you can see these are the attributes. I have A, B, C, D, E. These are the 5 attributes. So these are the columns. And in the rows, I will put the sub-relations. So there are R1, R2, R3. There are 3 sub-relations. Okay, these are the columns. This is the step number 1. You create a matrix. The step number 2, what is that? For every sub-relation, under its attributes, we will put the A entry. So R1 has ABC. Here I will put A entry. R2 has BCD. So here I will put A entries. And R3 has ACE. So here I will put A entries. Okay, is this clear? Very simple. Very simple. Now, what is the next step? So remember, so far, this is the step number 1 and step number 2. Step number 1, 2 are over. Okay, we have applied. Now let's apply the step number 3. What is that? That is the most easy and interesting step. That is apply the functional dependencies. Apply the functional dependencies. Apply the FDs. Okay, so let's apply the FDs. Now let's see. B determining E. This FD let's apply. First of all, what this FD means? This means that if two tuples have same B value, they must have same E value. Okay, you can easily see that. Look at these two tuples. They have same B value. So they must have same E value. Means in these two tuples, notice in these two tuples, we must have same E value. Okay. Remember one thing, this empty cell. Okay, here the value is unknown. We don't know whether this value is A or B or whatever. This value can be anything. This is unknown. Okay, but you can notice that these two tuples, they have same B value. So according to this functional dependency, if two tuples have same B value, they must have same E value. So you can see these two tuples have same B value. So these two tuples must have same E value. But I don't know what is the value. Okay, yes or no? Do you agree with me? These two tuples must have same E value, same value. Okay, these two tuples must have same E value. Now, we don't know what the value. So what should I do? I can put some value. Okay, I don't know what value, but I know that they must be same. I know they must be same. So I will put some value B. Okay, I can put some value, some random value you can put B1. Okay, no problem. Some random value you can put, no problem. But the point is they will be same. Okay, is this clear? Some random value you can put. Okay, now let's see. Again, what we will do, we will apply this FD, CE determining A. What it means? It means that whenever two tuples have same CE value, then they must have same A value. So which two tuples have same CE value? Notice one thing. Here CE value, here CE value, that is same. Yes or no? Because here also CE value is AB1, here also AB1. So whenever two tuples have same CE value, okay, like this first and second tuple, they have same CE value, AB1. So they must have same A value. I must have same A value in these two tuples. Okay, so what I will put, here value is A, so automatically here also value will be A. Okay, is this clear? Here also value will be A. Very simple. Okay, now again, repeatedly we will apply. Now let's apply this again, this B determining E. Again, let's apply this B determining E. So you can see whenever two tuples have same B value, they must have same E value. Now no changes will happen. Yes or no? In this table, no changes will happen if I apply this FD again. Let me apply this FD again. C determining E. Whenever two tuples have same CE value, they must have same A value. You can see this first and second tuples have same CE value. Okay, so they must have same A value. Again, no changes will happen. Now can you notice one thing? That in this table, I cannot make any changes. You can try. If you apply this FD, then also no changes. If you apply this FD, then also no changes. So if you apply the FDs, now there will be no changes. Okay. So now you can notice that now there are no changes and there is no row with all A entries. did you notice there is no tuple where all the entries are A? Like here we don't have all the entries are A. Here these are the missing entries. Okay, these are the missing entries. So here I don't have all the A entries, or I can say all the entries are not A. Similarly, here also all the entries are not A. Here also all the entries are not A. So now you can see that I cannot make any changes in this table. Also, there is no row where all the entries are A. Then in this situation, I can say lossy. Okay, you can easily notice that no more changes can be done. No more changes in matrix possible. In this matrix possible. Yes or no? No more changes in this matrix possible. So now you can stop and you can say so lossy, because there is no row with all entries A. Okay, is this clear? So you can see there is no row with all entries A. With all entries A. There is no row with all entries A, and there is no more changes possible. So automatically your answer will be lossy. I hope you understood. Okay, very simple. Now let's move on. Okay, so please focus here. Step number 4 and step number 5. After you apply the functional dependencies repeatedly, then remember, if we get some row with all entries A, then you can stop and say lossless. But remember, if there is no row with all entries A and no more changes possible, this is and, means you don't have any row with all entries A and no more changes are possible, then in this situation you can stop and you can say lossy. Okay, let's solve this question. This decomposition is lossy or lossless? Here you can see we have a relation R, functional dependencies are given to you, and we are decomposing this relation R into 5 sub-relations, R1, R2, R3, R4, R5. So these are the 5 sub-relations that we have. Now we want to check whether this decomposition is lossless or lossy. First of all, this is a non-binary decomposition. So what you should do, we must apply the chase test, yes or no? Because this is a non-binary decomposition, so we must apply the chase test. Okay, so let's apply the chase test. The chase test you already know. Okay, so let's apply this on this question. So first what you will do, you will create the matrix, yes or no? The step number 1, that is create the matrix where the columns will be the attributes. How many attributes are there? You can see there are 5 attributes A, B, C, D, E. Okay, so very simple that the columns will be the attributes A, B, C, D, E. And what will be the rows? The rows will be the sub-relations, yes or no? Okay, the rows will be the sub-relation. How many sub-relations are there? Total 5 sub-relations are there. So you can easily see that we have sub-relations R1, R2, R3, R4, R5. Okay, so these are the sub-relations that we have. Total 5 sub-relations you have. Okay, now what you will do? For every sub-relation, under its attributes, we will put the A entries. You can see R1 has attributes AD, so I will put A entry here, here. R2 has attributes AB, I will put entry here, here. R3 has attributes BE, I will put entry here, A entry here. Next, R4 has CDE. Okay, so A entry here, here, here. Next, R5 has AE, so I will put entries here. Okay, now what we will do? Now we will apply the FDs, yes or no? So this is what we have done. Remember, this is the step number 1 and 2. So far, here we have done the step number 1 and 2. Okay, now what we are going to do? Now we will apply the FDs, the step number 3 that you know, that apply FDs on this matrix. Okay, so let's apply the FDs now. You can see A determining C. What it means? It means that whenever 2 tuples have same A value, they must have same C value. Okay, so you can easily see that these tuples, they have same A value, so they must have same C value. Okay, but you can notice I don't know what is the C value. I know that they must be same. See, whenever 2 tuples have same A value, they must have same C value. You can see this tuple and this tuple. Okay, so these tuples, they must have same C value, right? But I don't know what is the value of C. So what I can do, no problem, you can put some B1, no problem. Okay, you can put a random value, some random value B1 you can put, there is no problem. Okay, but the point is very simple, that because in these tuples A value is same, so in these tuples C value also will be same. So you can put the value B1, no problem. Random value you can put B1. Okay, next you can see that B determining C. What it means? Whenever 2 tuples have same B value, they must have same C value. These 2 tuples have same B value, so they must have same C value also. Okay, yes or no? So you can see these tuples have same B value, so they must have same C value, and already this C value is B1 here, so this B1 I will put here also. Okay, let's apply this FD, C determining D. It means that whenever two tuples have same C value, they must have same D value. Yes or no? You can see that these tuples, look at these tuples, they have same C value, so they must have same D value. Okay, you can see that here D value is A, so this same D value I will put here. Okay, remember this same D value I will put here, here, here. Very simple. Next, okay, let's see which we can apply. So let's see this D determining C. What it means? D determining C means whenever two tuples have same D value, they must have same C value. Whenever two tuples have same DE value. Okay, remember. Okay, here can I say they have same DE value? Please tell me. Here can I say they have same DE value? No, please understand that these are the unknown values. They may be same, different, I don't know. So you cannot consider them same. These are unknown values. Okay, they may be same, they may be different, I don't know. So don't consider them as same. These are unknown values. We don't know what are the values. But you can notice that look at these tuples. They have same DE value. So according to this functional dependency, whenever two tuples have same DE value, they must have same C value. So here we have same DE value A. Okay, so these three tuples must have same C value. Means in these tuples, I must have same C value. But remember, we are interested in the A entries. So what we will do means B1, A, they are same because in these three tuples, D value is same. So in these three tuples, C value must be same. So B1 is equal to A. Yes or no? B1 is equal to A. And remember, we are interested in the A entries. We are not interested in the B1 entries. This B1, this is just a random value. We are interested in the A entries. So what we will do? B1 is equal to A. That is clear, right? B1 is equal to A. So I can remove B1 and I can put A. Because B1 is equal to A. This is what we found. That B1 is equal to A. Okay, so I can put A values now. Okay, what else? Did I get any row where all the entries are A? No, so far I did not get any row where all entries are A. Like this is unknown entry, this is unknown value, this is unknown value, this is unknown, this is unknown. So far I did not get any row where all the entries are A. Okay, so let's apply one more time. For example, now again let's apply this C determining D. This FD let's again apply. What this FD says, this say that whenever C value is same in two tuples, then D value also must be same. So yes, this is actually already fine. I cannot apply this. Okay, this is already applied, no problem. Next, what else we can do? Okay, let's apply this C determining A. CE determining A means whenever two tuples have same CE value, they must have same A value. Okay, so where do we have same CE value? You can see in these three. Look at this A. So you can see in these last three tuples, CE value is same. And you can see whenever two tuples have same CE value, they must have same A value. So in these three last tuples, CE value is the same. So in these tuples, A value must be same. Already A value is here A. So I should put A here also, here also. Okay, is this clear? So that's it. Now I can stop because remember I got this tuple where all the entries are A. Okay, notice this, that I got this tuple. Look at this tuple. In this tuple, you can see that all entries are A. And because all entries are A, so I can stop. Okay, yes or no? So I can stop and answer will be lossless. So this decomposition is lossless. I hope you understood. Okay, let's move on now. So we have seen the chess test. I hope this has become your favorite. Chess test is very interesting. Let's solve this GATE 2021 question. Consider a relation R, P, Q, S, T, X, Y, Z, W with the following functional dependencies. We are decomposing the relation R into, basically two decompositions are given to you. Decomposition 1, decomposition 2. Okay, so there are two different decompositions of R. Okay, and the question is asking which decomposition is lossless and which decomposition is lossy. You can notice one thing, that both the decomposition are non-binary decomposition. Yes or no? Okay, here also you can see in the decomposition D1, we are decomposing the relation R into four 4 sub-relations, yes or no? So this is a non-binary decomposition. Similarly, in the decomposition D2, we are decomposing the relation R into 4 sub-relations. So remember, here you can see that both these decomposition are non-binary decomposition. So we must apply the chase test, okay, to check whether these decomposition D1, D2, these are lossless or lossy. We must apply chase test. Okay, so let's apply the chase test. Let me tell you the steps of chase test. You can see quickly. In the chase test, what we will do, first we will create the matrix. Step number 1, that is create a matrix where the columns will be attributes and rows will be the sub-relations. In the step number 2, for each sub-relation under its attribute, we will put the A entries. The step number 3, that is repeatedly we will apply the functional dependencies in the matrix. Step number 4, if we get some tuple, some row with all entries A, then we can stop and we can say lossless. Step number 5, if there is no tuple with all entries A and no more changes are possible in the matrix, then you can stop and you can say lossy. Okay, so these are the steps in the chase test. Let's apply this. So one by one we will solve. First we will try for D1. First we will check for D1, then we will check for D2. Okay, let's check for D1. So you can see these are the functional dependencies in the original relation and this is the decomposition D1. Okay, so let's check. What I will do, I will create a matrix, right? Okay, so let me create a matrix. In the matrix, remember, the columns will be the attributes. How many attributes are there? You can see total 8 attributes are there. So I will create this type of matrix where the columns will be the attributes. Okay, total 8 attributes are there. So the attributes are like this. We have PQST. Next we have XYZW. Okay, so these are the columns that we got. Clear? Okay, now what are the rows? The rows will be the sub-relations. You can see in the decomposition D1 there are 4 sub-relations. Okay, PQST, PTX, QY and YZW. Okay, so I can call it like R1, R2, R3, R4. These are the sub-relations. What is the sub-relation R1? Sub-relation R1, remember, I am calling this PQST, this I am calling sub-relation R1. Let me call it sub-relation R1. Similarly, for example, this YZW, this I am calling it sub-relation R4. Okay, so you can see for every sub-relation under its attributes, we will put the A entries. So you can see R1 has PQST, so I will put A entries like this here. Next, R2 has PTX, R2 has PTX. Okay, R3 has QY, R3 has QY. Okay, and R4 has YZW. Okay, so now what we will do? Now we will apply the functional dependencies. Yes or no? Okay, so let's apply the functional dependencies. You can easily see this is very easy. Let's apply this functional dependency P determining Yx. What it simply means? It means P determining Y, P determining X. Okay, because remember every functional dependency I can split on the RHS that you already know. So if you have P determining Yx, this you can also write it P determining Y and P determining X. Okay, this is what you can do. So this FD I can rewrite P determining Y, P determining X. So you can see P determining Y. What it means? Whenever two tuples have same P value, they must have same Y value. So you can see these two tuples, they have same P value. Okay, so these two tuples, the first two tuples, they must have same Y value. Okay, so remember here the Y value will be same. But I don't know what is the Y value here. Yes or no? So I can put some random value like B1. Okay, now let's see the next. You can see P determines X. P determines X means whenever two tuples have same P value, they must have same X value. So these two tuples have same P value AA. So they must have, these two tuples must have same X value. So here X value is A. So here also I will put X value A. Okay. Next, let me apply this FD. Q determining Y means whenever two tuples have same Q value, they must have same Y value. Okay, so remember this tuple, they have same Q value. So this tuple, they must have same Y value. Means A is equal to B1. Yes or no? B1 and A, they are same. A comma B1, they are same. So what I can do, I can replace this B1 with A because we are interested in A. We are interested in the A entries. We are not interested in B1 B1 is a random value that we have taken. Okay, B1, B2, these are the random value that we can take. But we are interested in the A entries. Now you can see Q determining Y. It means whenever two tuples have same Q value, they must have same Y value. So you can see these two tuples, okay, this and this, these two tuples have same Q value. So these two tuples must have same Y value. So B1 is equal to A. So I can replace B1 with A. Okay, I can replace this B1, I can replace this, and I can put value A. Okay, like this. Very simple. Now let's see the next. Now we can apply this FD. Okay, that is PQ determining X. Means whenever two tuples have same PQ value, then they must have same X value. But no two tuples have same PQ value right now. No two tuples have same PQ value. Okay, so I cannot apply this FD. Okay, so forget about it. Let me apply this FD. Y determining ZW. Remember what it means? When I say Y determining ZW, that simply means Y determining Z, because we can split the FD on the RHS. Y determining Z and Y determining W. Okay, this is the meaning. So again, what I will do, remember, whenever two tuples have same Y value, they must have same Z value. So here you can see all the tuples have same Y value, so all the tuples must have same Z value. Here Z value is A, so all the tuples must have same Z value. Okay, similarly, Y determines W. Y determines W. So you can easily see that if two tuples have same Y value, they must have same W value. All the tuples have same Y value, so all the tuples will have same W value. So okay, so here also I will put A. Yes or no? Very simple. Now I can stop. I can stop because I got this row with all the entries equal to A. Yes or no? At this moment I can stop. Okay, so here you can see that this row I got. Okay, look at this tuple where I got all entries A. We got all entries A. So now I can stop and I can say that this decomposition is lossless. Okay, very simple. So remember, D1 is a lossless decomposition. This is what we have found, that this D1, this is lossless. Okay, and let's check about D2. Now we will check whether D2 is lossless or lossy. Okay, so let's check it. So you can see this is the D2 decomposition. Again, this is non-binary decomposition. We are decomposing our relation R into 4 sub-relations. Okay, so again what we will do, we will apply the chase test, because to check whether a non-binary decomposition is lossless or lossy, we should always apply the chase test. Okay, now in the chase test what we will do, we will create a matrix. In the matrix, remember that the columns will be the attributes. Total how many attributes are there? There are total 8 attributes. So the columns will be the attributes. Our attributes are PQRS. What are the attributes? The attributes are PQST, XYZW. Okay, PQST, XYZW. Okay, so these are the columns. Columns are the attributes. And what are the rows? Rows are the sub-relations. You can see there are total 4 sub-relations. This PQX, let me call it R1. And this YZW, let me call it R4. So you can see there are total 4 sub-relations. R1, R2, R3, R4. Okay. Now what we will do, the next step, for every sub-relation under its attributes, we will put the A entries. So R1 is PQS, so I will put A entries here. Next, what is R2? R2 is TX, so I will put A entries here. R3 is QY. R3 is QY. And what is R4? That is YZW. That is YZW. Okay, so very simple. So this is the matrix that we got. Okay, now what we will do? Now we will apply the functional dependencies. So let's apply the functional dependencies. Okay. Now you can easily see that this is a P determining Yx. What it means? Whenever two tuples have same P value, they must have same Yx value. Okay, but here you can see no two tuples have same P value. So right now we cannot apply this FD. So let me apply some other FD. For example, let me apply this FD, Y determining ZW. Let me apply this, because remember, when I say Y determines ZW, what it actually means? Y determines ZW. This FD, I can split on the RHS. This simply means that Y determines Z and Y determines W. Okay. So remember, this FD means that whenever two tuples have same Y value, they must have same Z value. Okay. So you can see these two tuples, they have same Y value. these tuples, they have same y value. So these tuples, they must have same z value. Here z value is a, so here also I will put the z value a. Next, these two tuples have same y value, so they must have same w value. Okay, here the w value is a, so here also I will put the w value a. Very simple, right? Okay, so now let's apply the next FD. For example, next I can apply q determining y. Okay, means two tuples, if they have same q value, they must have same y value. Yes or no? Now you can notice this tuple, they have same q value, so they must have same y value. This tuple, they must have same y value. So you can see this value also will be a. Okay, so very simple, I will put this value a. Okay, what else I can apply? Now let's see, can we apply some other FD? You can see again I can apply y determining z. Again I can apply this FD. Okay, again apply this y determining z. Again apply this. Whenever two tuples have same y value, they must have same z value. So you can see, look at these three tuples, they have same y value, so they must have same z value. Okay, and remember, they must have same w value because y determines w. So I can say that here also I will put a, here also I will put a. Okay, now let's see what else I can do. Again, now I cannot apply this FD, no more changes will happen. If I apply this FD, no more changes will happen. Yes or no? If I apply q determining y, then no more changes will happen. Because of this FD, no more changes. Because of this FD, no more changes. Because of this FD, no more changes, because no two tuples have same p value. So because of this FD, no more changes. Because of this FD also no more changes, because no two tuples have same pq value. You can see no two tuples have same pq value. So no more changes I can do. Now you can notice at this moment, whatever FD you apply, no more changes you can do. And also there is no tuple with all entries a. So I can stop and I can say this is lossy decomposition. Is this point clear? So please notice that there is no row with a entries. There is no row with all entries a. All entries a. And no more changes. Now no more changes possible. Yes or no? No more changes possible. So in this situation, when there is no row with all entries a, and there is no more changes possible, in this situation I can stop and I can say that this decomposition is lossy. Okay, so that's it. Finally I can say that our decomposition D2, that is lossy. D2 is lossy and D1 is lossless. So the answer will be D1 is lossless, D2 is lossy. So answer will be option A. The question is asking the correct statement, so the option A will be the answer. Like this you can solve this question. I hope you understood. So please tell me, the chase test, is that comfortable? This is very easy, very interesting topic. I hope you understood. Okay, so far anyone has any doubt, let me know. Please tell me, so far anyone has any doubt, let me know. So far everyone understood everything? Okay, one last topic is remaining now, so let's finish that also. The next topic that we study, that is redundancy and normalization. Redundancy, the name itself is telling you redundant data. Basically we are storing the redundant data, same data we are storing many times, that is called redundancy. And this is a very obvious thing that we don't want redundancy. Yes or no? Same data we don't want to store at multiple times at multiple locations. Okay, so redundancy is not desirable. We want to reduce redundancy. Okay, and let me tell you, to reduce redundancy, what we do normalization. So let's see the definition of redundancy and normalization. So what is a bad database design? That is very simple. That is redundant storage of information. Same information we are storing many times in multiple places. So that is called redundant storage of information. And this is very obvious, very intuitive, that we don't want redundancy. Yes or no? Redundancy is not desirable. Because of redundancy, what happens? Many problems can happen. Like when you insert the data, when you delete the data, when you modify the data, then because of redundancy, a lot of problems can happen. Okay, so we want to reduce the redundancy. We want to reduce data redundancy. Okay, this is what we want to do. So how to do that? how to reduce data redundancy, and for that the answer is normalization. Okay, so remember this redundancy, this is the problem, and the solution is normalization. Okay, redundancy means redundant storage of data. We don't want that. We want to reduce the redundancy, so the solution is normalization. Now let's see what is normalization. What the definition of normalization? So normalization means this is a process to convert our database into higher normal forms by decomposing the large tables into smaller tables. This is the definition of normalization. Okay, so let's understand the definition of normalization. The purpose of normalization you understood. We want to reduce data redundancy. That is the purpose of normalization. Now, what is normalization? Normalization is a process, remember. It is a process to convert our database into higher normal forms by decomposing, by dividing the large tables into smaller tables. Okay, this is called normalization. Okay, so let me tell you, like these are the normal forms that we study: 1NF, 2NF, 3NF, BCNF, and when we go in this direction, then we are getting the higher normal form. Means this BCNF, this is higher normal form than 3NF. Okay, so let me tell you here few things, that when we go in this direction, then we are going in the higher normal forms. Okay, in this direction we are getting higher normal forms. Higher normal forms. For example, this BCNF, this is among all these, this is the highest normal form. This BCNF, among all these normal forms, this is the highest. It is highest normal form. Okay, is this clear? Among all the normal forms that we are writing here, like 1NF, 2NF, 3NF, BCNF, among all these normal forms, basically this is the highest normal form. Okay, so when you go in this direction, then we are getting higher normal forms. And also let me tell you, when you go in this direction, then we are getting weaker normal forms. Weaker normal forms. Okay, is this clear? For example, this is the weakest normal form. Okay, this 1NF, this is the weakest normal form. And also let me tell you that I told you the definition of normalization, yes or no? What the definition of normalization? Normalization is a process to convert the database into higher normal forms by decomposing large tables into smaller tables. Okay, so if you are doing the normalization, then basically what you are doing, you are converting your database into higher normal forms. Okay, so remember, when you go in this direction, then remember the redundancy will reduce. In this direction, what will happen? The redundancy reduces. Okay, when we go in this direction, means if you convert your database into BCNF, then I can say redundancy will reduce. Okay, let's assume that your database is in first normal form. Now if you convert this into second normal form, then redundancy will reduce. Okay, if you convert 2NF into 3NF, then redundancy will more reduce. If you convert 3NF to BCNF, then more redundancy will reduce. The point is, in this direction, the redundancy will reduce. Okay, let's see one example. Consider this table. You can see this table is not in the first normal form, because you can see this cell. In this entry, we have set of values. Okay, you know the definition of 1NF. What the definition of first normal form? 1NF says that every table cell should contain single value. Yes or no? In the table, every cell should contain a single value. But here, if you notice, look at this cell. In this cell, we have multiple values. So this table is not in 1NF, or I can say this is the 1NF violation. Okay, the definition of 1NF you already know, that in 1NF, remember, we disallow, the first normal form disallows the multi-valued attributes. We don't allow multi-valued attributes. Okay, we don't allow composite attributes. And remember, what we don't allow set of values. Yes or no? 1NF does not allow set of values. Basically, in every cell, in every table cell, we should put a single value. Okay, so you can easily see that because of this is a set of values, or I can say these are the multiple values. This is set of values, or I can say basically you are putting multiple values. Multiple values. So this table, at this moment, this table is not in first normal form, I can say. So this table is not in first normal form. Okay. And you tell me one thing. This table is not in the first normal form, that is fine. But a simple question I'm asking, in the real life, this type of table is possible or not? See, this type of information is possible or not? This table is not in the first normal form, but in the real life, this type of information is possible. For example, this is the album number. Okay. And this album number has multiple artists. Okay. Yes or no? And this can happen in the real life. In the real life, the same album can have multiple artists. Yes or no? Do you agree with me? So remember, this is a real world information. Means in the real life, this type of information is possible, that this album number has multiple artists. But remember, we cannot put all these artists in the single cell. I told you that this table is not in first normal form, because in the first normal form, in every cell we put single value. So this album has multiple artists, that is fine. In the real life, a single album can have multiple artists. It is possible in the real life, but we cannot put all these values in the single cell. So tell me how to convert this table into first normal form. Very simple. If you want to convert this table into 1NF, then what you will do? You will split basically split this tuple, this row you will split into 4 rows. Okay, for every artist you will create one row. So basically this is what you are going to do. You can notice here that we are going to split. You can notice this album, this BTL007, this album, you can notice we are splitting into 4 rows. We are splitting into 4 rows. For every artist we are creating one tuple. Now this table is in the first normal form. Okay, is this clear? So now this table is in the first normal form, but now there is redundancy. Okay, in this table there is redundancy. Can you find where is the redundancy? Can anyone find where is the redundancy? The redundancy is very simple. You notice one thing, that look at this album. Okay, for this album, remember, for this album, this is the price. So if I repeat this album 100 times, then this price will repeat, and that is redundancy. If I repeat this album, let's assume this album number, if I repeat, let's assume 1000 times, then this price will also repeat 1000 times. This is unnecessary. This is a redundancy, that because we are repeating this 1000 times, so this is also repeating 1000 times. Okay, so this is redundancy. So this is what I'm saying, that this table is in the first normal form, because every cell has single value now. Okay, in every cell there is single value, so this is in the first normal form, but there is data redundancy in this table. And where is the data redundancy? You can see the data redundancy, because for this album the price is 23. Okay, you can see this same value is repeating, this same, because this album is repeating. You can see this album is repeating, so this price is also repeating. Now just think about it. If this album number, if this repeats, let's assume 1000 times or 10,000 times, then this price will also repeat 10,000 times, and that is unnecessary. Okay, yes or no? So this is called data redundancy. I hope you understood. There is data redundancy in this table. Okay. Now how to reduce this data redundancy? That is a simple question. How to reduce? Okay. To reduce this data redundancy, what you can do? You can split this table. You can decompose this table. Okay. There is data redundancy. To reduce that, what I can do? See, very simple thing I can do. I can decompose this table. In one table, I will put this album number, artist name. Okay, this I will put in one table. Let me call it table T1. And in another table, what I will do? In another table, what I will do? In another table, I will put this album. See, in another table, I will put album number and price, stock. So basically, what I'm going to do, to reduce the redundancy, I will split our database into 2 tables. Okay, I will split this table. I will decompose this table into smaller sub-relations. You can see. So 2 sub-relations I got. You can notice. Now in this table I have our album number, artist name. Okay, and in this table I have album number, price, stock. Now you can see there is no redundancy. Okay. One more thing. Some students might be thinking, sir, again I have redundancy because this album is repeating 4 times. This album number, look at this album number. This is repeating 4 times. So can I say this is redundancy? Can I call it redundancy? No, this is not redundancy, because remember, this is the information that for this album number, this is the artist, this is a different 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 artist. So remember, this is not a redundancy, please understand. Because here we are giving the information that this album number has 4 different artists and what are their names. Okay, so this is not data redundancy. Compare this situation with this price situation. Okay, in this price situation, what is happening? If this album number repeats 1000 times, then the same price will repeat 1000 times. This is redundancy. Okay, means if I am repeating this attribute 1000 times, this value, if I repeat 1000 times, then this value will also repeat 1000 times. This is data redundancy. Okay, but focus here. Here we don't have any data redundancy, because if I am repeating this album number, this is not a redundancy. This is not a redundancy. Why? This is not redundancy because I am getting the information that, okay, that for this album number there are 4 artists and I am giving their different names. You can see all these 4 rows, they have different 4 artist names. Okay, so this is not a data redundancy. Okay, now let me tell you, at this moment our database means both the tables. Okay, when I say database, it means all the tables. Now you can see at this moment our tables are in the BCNF. Okay, and because our tables are in the BCNF, these are free from redundancy caused by functional dependencies. Okay, at this moment there is no redundancy because of functional dependencies. Okay, so this is the idea. I hope you understood the definition of normalization. Okay, now we will see some important points about redundancies. So far what we have seen, let me tell you, we have seen the definition of redundancy and also the definition of normalization. If you did not understand something, don't worry about it. That is just to make you understand what is redundancy and what is normalization. Normalization is a process to reduce redundancy. Yes or no? In the normalization, what we do? In the normalization, we decompose the large tables into smaller tables, and basically we convert our database into higher normal forms to reduce redundancy. Okay, the purpose of normalization, that is to eliminate, or I can say reduce, redundancy. Now the next topic is some important points about redundancy. So let's see. The first point, trivial functional dependency, they can never create redundancy in the database. The reason is very simple, because these are trivial. They will always hold in every relation. Okay, remember, trivial functional dependency, the name itself is telling you these are trivial. They will always hold in every relation. They are always satisfied by every relation. So trivial functional dependency can never cause redundancy, in the database. So who will create redundancy in the database? Very simple. Non-trivial functional dependencies, they may create redundancy in the database. Not all non-trivial functional dependency create redundancy. I will tell you which one create and which one do not create. I will tell you. But the point is, trivial functional dependency never create redundancy in the database. Non-trivial functional dependency may create redundancy in the database. Okay. For example, consider this table. In this table, did you notice one thing? This album number determines price. Okay. Yes or no? Album number determines price in this table. Album number determines price, and you can see album number, that is not a super key, because you can see here in these 4 tuples the album number is repeating. Okay, this album number is repeating. So you can see album number, this is not a super key. Actually, what is the super key? The super key is this combination. Okay, the super key is this combination. So remember, album number, this is not a super key. This is not a super key. Album number is not a super key. Who is the super key then? Who is the primary key? Who is the super key? The primary key is album number, artist name combined. Okay, so let me tell you here. Here the primary key. Here the primary key is album number dot artist name. Okay, so remember, this is the primary key. Okay, is this clear? Because you can see album number, that is not a candidate key, that is not a super key, because you can see this value is repeating. Okay, and you can easily notice that album number determines price. So if I repeat this album number, this value, if I repeat 1000 times, 10,000 times, 1 crore times, then this price value will also repeat 1 crore times. Yes or no? Because the definition of functional dependency, remember, this functional dependency, what it means? It means that whenever 2 tuples have same album number, they will have same price. Yes or no? So you can see, if this album number repeats 1000 times, then the same price will repeat 1000 times. Okay, yes or no? So you can see because of this functional dependency, this is a non-trivial functional dependency. Notice one thing. Okay, because of this non-trivial functional dependency, there is redundancy in the table. Okay, I hope you understood. Now let's see the next point. So you can see that non-trivial functional dependency may create redundancy in the table. Another example you can take, for example, a student table. In the student table, you have these attributes: student ID, name, DOB, state, and district. You know that district implies state. This functional dependency is there. Yes or no? This is a non-trivial functional dependency. So you know that there is a non-trivial functional dependency here, non-trivial FD, that district determines state. If you know the value of district, then you automatically know the value of state. If two tuples have same district, then they must have same state. Yes or no? So you can see this is a functional dependency. This is a non-trivial functional dependency. And you can notice because of this non-trivial functional dependency, there will be redundancy. Why? Because if you repeat, for example, Jaipur 1000 times, okay, in this student table, if Jaipur repeats 1000 times, Jaipur 1000 times, then Rajasthan will also repeat 1000 times. Yes or no? So that is the reason I am saying that because of this non-trivial functional dependency, in this table, we will get redundancy. Okay. So non-trivial functional dependency may create redundancy. Now one more interesting point. Non-trivial functional dependency where LHS is a super key, they will never create redundancy in the database. Non-trivial functional dependency where LHS is a super key, these non-trivial functional dependency, they never create redundancy in the database. And the reason is very simple. Because if you have a non-trivial FD, X determining A, okay, where X is a super key. Let's assume X is a super key. Now let me tell you, because of this functional dependency, there will be no redundancy in the table. The reason is very simple, very intuitive, because if X is a super key, then X cannot repeat any two tuples. Yes or no? In any two tuples, the X value can never repeat. Do you agree with me? Okay, so remember, X can never repeat any two tuples because X is a super key. So all these values, these will be distinct. All these X values, these will be distinct. Okay, yes or no? So this is what I'm saying, because this is a super key, because this X is a super key. So this cannot repeat in any two tuples. In any two tuples, in any two rows, this can never repeat in any two rows. Okay, very simple. So this is what I'm saying, that non-trivial functional dependency where LHS is a super key, they never create redundancy in the database. I hope you understood. Now you tell me one thing. In the BCNF, can we get redundancy because of functional dependency? In the BCNF normal form, can functional dependency create redundancy? The answer is no. Because remember, in the BCNF, either we have trivial functional dependency, and you know that trivial functional dependency will never create redundancy. Okay, also in the BCNF, we know that whenever there is a non-trivial functional dependency, X determining A, then X will be a super key. Okay, in the BCNF, remember this point, in the BCNF, the LHS of every non-trivial functional dependency is a super key. Okay, so you can notice that in the BCNF, the LHS of every non-trivial functional dependency is a super key. So functional dependencies can never create redundancy in the BCNF. Do you agree? Very simple point. So I am telling you that BCNF is 100% free from redundancy caused by FDs. Okay, in the BCNF, FDs can never create redundancy. Okay, BCNF has 0% redundancy created by FDs. So remember, BCNF is 100% free. 100% free because of redundancy caused due to FDs. Okay, so this is an important point, that in the BCNF, functional dependencies, FDs cannot create redundancy. Maybe some other thing can create redundancy. Remember, in the relation, we have functional dependency is a concept. Yes or no? Functional dependency is one concept. There are other concepts also. So maybe there is redundancy because of some other reason. But the point is, BCNF does not have any redundancy because of functional dependency. Okay, this is the important point, that BCNF does not have any redundancy. BCNF has 0% redundancy because of functional dependencies. So you might be thinking, is BCNF free from all the redundancy? Can I say that BCNF does not have any redundancy? The answer is no. The answer is no, because remember, there may be some other reason for the redundancy, but functional dependency is not the reason. This is what I'm saying. In the BCNF, there may be some other reason for redundancy. There may be some other cause of redundancy, but functional dependency, FDs can never create redundancy in the BCNF. So BCNF is 100% free from redundancy caused due to functional dependencies. There may be some other reason for redundancy that may be possible. So remember, you cannot say that BCNF is 100% free from all the redundancy. No, you cannot say. There may be some other reason for the redundancy. There may be redundancy that are not caused by FDs. Okay, caused by some other mean. Okay, let's see this point, that BCNF is 100% free from redundancy created by FDs, but 3NF may have redundancy created by FDs. Okay, in the 3NF, we may have redundancies created by FDs. Okay, now let's move on. Let's solve this GATE 2002 question. A relation R with associated set of functional dependencies F is decomposed into BCNF. Okay, the redundancy arising out of functional dependencies. The question is asking that the redundancy which is created by functional dependency, which is caused by functional dependency, what can you say about it? Very simple. This relation R we are decomposing into BCNF. Now our database is in BCNF, and I told you that BCNF has 0% redundancy created due to functional dependency. Okay, so for this question the answer will be option A. The answer will be option A, 0. BCNF has 0% redundancy caused by functional dependency. But remember, BCNF may have redundancy caused by some other things, some other means. Let's see the next topic, that is 3NF decomposition and BCNF decomposition. This is a small topic, so let's see. If you have a database, what is a database? Database means set of tables. In our database, we can have many tables. Okay, so remember, database is set of relations, or I can say database is set of tables. For example, consider this database as, this is our database. This is our database where this R1 is a table. This is a table. This R1 is a table, this R4 is a table. So in our database, let's assume there are 4 tables. Now tell me, when can I say my database is in BCNF? When can you say that my database is in BCNF? Okay, very simple. If you want to say that your database is in BCNF, then every table should be in BCNF. Very simple idea. Okay, so very simple. A database is in BCNF if and only if each relation is in BCNF. Okay, so this is a note, remember. A database means set of relations. Okay, in our database we can have many tables, so a database is in BCNF if each table is in BCNF. Similarly, a database is in 3NF if each table is in 3NF. Similarly, a database is in 2NF if each table is in 2NF. Okay, now let's move on. Tell me the answer for this question. If R is not in BCNF, there is a relation R which is not in BCNF, then how to make it into BCNF? I told you the answer. What we will do, if R is not in BCNF and you want to convert into BCNF, then you can decompose R such that every sub-relation is in BCNF. Yes or no? Okay, so this is the answer. If you want to convert this relation R into BCNF, then what you will do? You will decompose this relation R. We will decompose this R into sub-relations such that every sub-relation will be in BCNF. This is what we are going to do. And this is called BCNF decomposition. Okay, what is BCNF decomposition? Very simple. You have a relation R which is not in BCNF. Then what we can do? We can decompose this R into sub-relations such that every sub-relation is in BCNF. This is called BCNF decomposition. This is the definition of BCNF decomposition. Very simple. If your relation is not in BCNF, then what we will do? We will decompose the relation into sub-relations such that every sub-relation is in BCNF. This is called BCNF decomposition. So let's see the definition of BCNF decomposition. A decomposition in which every sub-relation is in BCNF. Similarly, what is the definition of 3NF decomposition? 3NF decomposition. It means a decomposition in which every sub-relation is in 3NF. Okay. Now let's see some important points about 3NF and BCNF decompositions. from these important points the questions have come in the GATE exam. Okay, so let's see some important points regarding 3n of decomposition and BCN of decomposition. This is the important point. For every relation, whatever relation R you take, there always exists at least one decomposition which is 3n of and lossless and dependency preserving. Means take any relation. For every relation R, there exists at least one decomposition. For every relation R, there is some decomposition. There is at least one decomposition which will be 3n of also, which will be lossless also, which will be dependency preserving also. Basically, for every relation R, these three things are possible. Okay, means every relation R I can decompose such that these three properties I will get. I will get 3n of, every subrelation will be in 3n of, and the decomposition will be lossless, and the decomposition will be dependency preserving. All these three properties I can get. Okay, is this clear? But remember, for every relation R, if you decompose into BCN of, okay, then remember, for every relation R, there exists a BCN of decomposition. There exists a decomposition such that we will get BCN of subrelations and it will be lossless. But it may or may not be dependency preserving. Okay, is this clear? It is not guaranteed to be dependency preserving. Okay, so this is the simple point. Let's see. This is what I'm saying, that every relation R can be decomposed into subrelations, into a set of relations such that all these three properties we will get. Which three properties? Every subrelation will be in 3n of, the decomposition will be lossless, and the decomposition will be dependency preserving. So remember, for every relation, this type of decomposition we can get. For every relation R, there is some decomposition which will give you all these three properties. It will give you 3n of also, all the subrelations will be in 3n of also, your decomposition will be lossless, and your decomposition will be dependency preserving. So all these three properties, if you want to get, it is possible. Is this clear? If you want to get 3n of, lossless, dependency preserving, if these three properties, if you want to get, then it is possible for every relation. Okay, is this clear? Very simple point. So you can read this, that for all the relations, for every relation, lossless, dependency preserving, 3n of, these three properties, this type of decomposition is always possible. Okay, you can see every 1NF relation can be has a decomposition. Every 1NF relation has a decomposition, has at least one decomposition in 3NF relations, which is lossless also and which will preserve the dependency also. Okay, now let's talk about BCNF. I told you that if you want to convert into BCNF, then lossless you can get. Lossless BCNF decomposition you can always get, but dependency preservation may not be possible. Okay, so read this. For every relation, lossless BCNF, this type of decomposition is always possible, but dependency preservation may or may not possible. Okay, for some relations, remember, there are some relations for which if you want all the three properties, you want lossless also, dependency preservation also, and BCNF also. If you want all the three properties, then that may not be possible. So there are some relations for which there is no decomposition, which will give you these three properties. Okay, is this clear? I hope you understood. So remember, there are some relations for which there is no decomposition. There is no decomposition which will give you all the three properties: BCNF, lossless, and dependency preservation. Okay, so there are some relations for which there is no such decomposition which will give you all the three properties simultaneously. I hope you understood. So let me tell you this point. Let me make the summary of all these important points. The summary is like this. See, you can take any relation R. Okay, you can take any relation R. Whatever relation R you take, then remember, there exists a decomposition. There exists a decomposition. I am saying that there exists a decomposition. For every relation, you can take any relation R you can take, there exists a decomposition such that all these three properties you will get. Okay, you will get 3NF also. Every subrelation will be in 3NF also. Okay, 3NF subrelations. 3NF subrelations. Okay, the decomposition will be lossless. and the decomposition will preserve the dependencies. Okay, I hope you understood. So this will happen for every relation. When I say any relation, it simply means I am talking about for every relation this will happen. For every relation R, if you want a decomposition such that these three properties will be satisfied, then this type of decomposition is always possible. Okay, for every relation, this type of decomposition is always possible. Okay, now let's see what about BCNF. Now see, if you want BCNF decomposition, if you want sub-relations which are BCNF, if I want BCNF sub-relations, then remember, I can get lossless, but dependency preservation may not be possible. Okay, is this clear? These two properties I can get for every relation. For every relation R, these two properties I can get. This type of decomposition I can get where the sub-relations will be in BCNF and it will be lossless, but dependency preservation may not be possible. Okay, so I am telling you that there are some relations, not all, there are some relations R such that there is no decomposition. Where all these three properties you can get simultaneously, that you can get BCNF also, lossless also, dependency preservation also. Okay, such that you can get BCNF also and you can get lossless also and you can get dependency preservation also. Okay, is this clear? There is no decomposition which will give you all these three properties simultaneously. Okay, but remember, for some relations you can get. Okay, yes or no? For some relations you can get. When I say some relations have no decomposition, then other relations have. Yes or no? So some relations, remember, please understand, there are some relations for which you can get all these three properties. Okay, for some relations you can get all these three properties. For some relations you cannot get all these three properties. But if you want to get these two properties, then that is always possible. BCNF, lossless, that is always possible. For every relation there exists a decomposition which will give you these two properties, lossless and BCNF. Okay, let's solve this question. This is GATE 2005 question. Which of the following statement are false? The question is asking false statement. BCNF is stricter than 3NF. This statement is actually true. Yes or no? Because every BCNF relation is actually 3NF. So BCNF is more strict than 3NF. Yes or no? You know that every BCNF relation is 3NF. But there are 3NF relations which are not BCNF. Okay, so BCNF is more strict than 3NF. This statement is actually true. Now, any relation with two attributes is in BCNF. This we have already seen in the previous lecture. This statement is also true. You can find the link in the description. Let's see this. Lossless dependency preserving decomposition into 3NF is always possible. Yes, this is always possible for every relation. For every relation, this is always possible. What about this? Lossless dependency preserving decomposition into BCNF. This is always possible. This is false. This is false. The question is asking false statement, so the answer will be option C. This is GATE 1994 question. State true or false with reason. There is always a decomposition into BCNF that is lossless and dependency preserving. This statement is false. Yes or no? Because there are some relations for which there is no decomposition which will give you all these three properties simultaneously: BCNF, lossless and dependency preserving. So you can see the question is saying there is always a decomposition into BCNF which is lossless and dependency preserving. This statement is a false. This statement is actually false. Okay, is this clear? This is false. Now let me ask you some variations of this question. In the same question, if they ask you, let's assume they remove the dependency preserving. Now what about the answer? Now they are asking you that there is always a decomposition in BCNF which is lossless. Yes, this statement is true. Okay, for every relation, this type of decomposition you can get where BCNF and lossless, these two properties are satisfied. So now this statement is actually true. Okay, and what about the same statement for 3NF? The same statement, if I make for 3NF, the third normal form, then this statement will become true. Okay, for 3NF, now this statement actually will become true. This is nearly 2018 question. Identify the true statement. Any relation with the two attribute is BCNF. This we have already seen in the previous lecture. This statement is actually true. Any relation with the two attribute, that is always in BCNF. Lossless dependency preserving decomposition into 3NF is always possible. Yes, that is always possible. Okay. So both the statements are true. Answer will be option C. Let's answer the last question. This is the last topic. Which normal form is adequate and nice and preferred? We have seen 1NF, 2NF, 3NF, BCNF. Okay. Now among these normal form, which normal form is most preferred? Or I can say which normal form is overall nice, adequate and preferred? So the answer is 3NF. Okay, let me tell you, the answer is 3NF. What is the reason? The reason is very simple. Because for every relation R, you can convert that relation R, you can convert your database into 3NF such that you get lossless also, lossless decomposition also, you get dependency preservation also. So basically 3NF is overall nice normal form where you do not lose any property. Okay, you do not lose the data, you will get lossless joint decomposition. You do not lose any functional dependency, you will get dependency preservation decomposition. So you can see 3NF is overall nice. But remember, if you go for BCNF, then maybe you can lose dependencies. Yes or no? If you go for BCNF, remember, then you may lose dependencies. Functional dependencies you may lose. So that is the reason overall 3NF is preferred. Okay, so the same thing is written here, that if you go for BCNF, then you may lose dependencies. Dependency preservation may not be guaranteed. You can easily see it is not always possible to have a BCNF design that is also dependency preserving. Yes or no? It is not always possible to have a BCNF design which is dependency preserving. So overall, what people do, what people usually do, they hold on to dependency preservation and they give up the BCNF. So basically, people don't want to lose dependencies. Okay, we don't want to lose dependencies. We want dependency preservation also. We want lossless decomposition also. So that is the reason overall 3NF is a good way. Okay, is this clear? This is GATE 1998 question. Which normal form is considered adequate? Which normal form is considered to be adequate? So the answer will be 3NF. 3NF is considered to be adequate. Okay. So that's it. This is your chapter. We have seen everything about decomposition. We have seen decomposition definition, lossless, lossy, dependency preservation. We have seen the chase test for binary decomposition, how to check whether it is lossless or lossy. For non-binary decomposition, how to check lossless or lossy. Okay, we have seen the projection of functional dependencies on a subset of attributes. We have seen the BCNF decomposition, 3NF decomposition. We have seen redundancy and normalization. Okay, this is all in one lecture. Let me tell you, in this lecture, each and everything related to related to decomposition, related to 3NF decomposition, related to BCNF decomposition, okay, lossless, lossy, anything. All these concepts we have seen. I hope you loved this session. Please share your feedback in the comments. That will mean a lot. Okay, that will motivate me a lot. Okay, so a long session I have taken. You can see without any unnecessary talk. You can see in this session from the beginning till the end, I did not do any unnecessary talk. Only concepts we have seen. Okay, a lot of practice we have done. Each and every concept we have seen. And I hope you loved this session. Please share your feedback in the comments. That is very important. Okay, please share your feedbacks. Okay, thank you everyone.